Nice.
Hey Arpit, am I audible now?
Yeah, you are. Ajay, you are
Oh,
speaking. Yeah, Vamshi.
yeah, I was speaking, but somehow I was on my Bluetooth headset. Somehow the microphone was not working.
Yeah.
I was like surprised. Like even in the last session, I was speaking sometimes, but I don't know. I thought like, okay, too many people are speaking. We would have
Nah,
missed.
nah. Bro. You have never been audible. Your
Yeah,
voice never reached us.
yeah. I mean, I just fixed it now. I was just checking the settings in Zoom, so I just realized my microphone was connected to the system, which didn't had a microphone.
And I was
So.
wondering why you were not speaking. I know how
Yeah,
talkative you can be.
yeah, true that. How are you doing, Arpit?
I'm doing
So
very
I
well.
joined early just to have a word with you. It's been a while. I mean, we had spoken, right?
Yeah,
So
long
I
time.
joined early, like as soon as you pinged, but somehow I had a trouble connecting through Zoom. So
Yeah.
by
We'll
the
catch
time
up
I
anytime.
joined,
We'll catch
yeah,
up after the course. Well, after the session.
yeah, sure. So much to speak, so much to
Yeah,
ask.
yeah, yeah, yeah.
So,
Nice. Next course. How many people?
Triple IT also has a decent Python community, right? वो conference होते थे.
वो तो मतलब chill है मतलब nothing major. It's just
हम्म.
there. मतलब people are always motivated, but you know when job internships and companies come in, everything takes a backseat.
हाँ
तो वो
हाँ
थोड़ा ऊपर नीचे हो जाता है
हाँ,
कभी कभी.
priorities. Yes.
Priorities. That's
yeah,
the harsh reality.
but I see that we had a very good community of people who used to do competitive programming mainly in Python. Um,
Yeah.
Python में competitive, nice.
That was really strange when I got to know about it. So
नहीं, मुझे
people.
लगता है खाली मैं ही करता हूँ.
नहीं नहीं बहुत लोग करते हैं वहाँ बहुत लोग करते हैं and they gain performance out of it so I vaguely remember there was this code that they added as a monkey patch which is
हम्म.
to speed up things so even a bad code because with Python they used to increase the limit from a second to 3 seconds
हाँ, वो रन टाइम
right
पे इशू है ही.
so then they used to patch those things so that even a bad code gets accepted.
Oh, nice.
Yeah, hacks
Monkey
everywhere.
patching कहीं तो यूज हुई.
I monkey patched a couple of libraries. I forgot to tweet about it. Yeah, I forgot to tweet about it. So monkey patching for the first time I used monkey patching. So I had to alter a library instead of forking that library and basically so basically instead of forking that library, making that change, adding to the commit and then making an entry in requirements.file. What I did was I just did a monkey patch. It was just a one-line change. So I just ran a monkey patch and just alter the function. It was for web scraping something to get all the links from sitemap. So it did not have a certain function. So I just so it had a function signature, but the body had a bug. So I just monkey patched the code there, and then it worked. And basically this is the first time when I used monkey patch, and I was so happy that finally a genuine use case of monkey patch.
That's what I was saying. I haven't seen monkey patch used anywhere else,
Yeah.
at least not
Monkey
in
patch is
production.
typically used for जो है वो Python 2 to 3 migration and बस ऐसी दो तीन जगह. It's normal people using monkey patches. Okay, I'll share the screen. Chalo, let's start with this week's agenda. Is Arpit audible? Varun? Umang serious, thanks a lot. Varun, you might want to. Acha, you're audible. क्या पता. ठीक है, चलो. I hope issues get resolved. We'll start with the week with database. Today, what we'll be looking at is. Acha, by the way, did you all receive email regarding week two's agenda? I dropped in your
Yes.
week, na? हाँ, ठीक है. I've never seen this issue with my past code. Not sure what's happening with this one, but there are some really vague issues. But okay, hope that gets cleared out. Okay. So this week will be today we'll be talking. Sandeep, I didn't receive. I dropped an email on Google group wala thing immediately on Monday. Uh, and also the steps on and also dropped everyone a personal email on how can you enable that. So Sandeep,
Yeah,
please check.
I mean,
Hmm.
I got that mail like how to change that settings in
Uh,
Google Groups, but I didn't got any mail.
everyone got it. What's happening with Google group?
Okay, I think let me check that
Just
out.
just check your preference. Just go through the Google group wala page. From next time I'll also put it on Discord as well. All
Okay,
the
okay,
places.
yes.
I'll do that. So and anyway the agenda is mostly which is displayed on my website. So typically that would be the agenda. So you can anyway refer to that. So there is nothing extra that obviously the extra thing would be covered, but basically that would be the primary outline of it. And so you can always refer to that. Sure. So today what we'll be talking about is relational databases. So there is so many things to talk about with respect to relational databases. Obviously relational databases are the most common ones, heavily used in industry. The primary reason why relational databases are so famous is because it has ACID properties. We will come to that. But just before that, a few things that are really critical when you design a system is about understanding the normal forms, right? So with respect to relational databases, we store everything in terms of rows and columns. So it is typically a ledger. So typically your Microsoft Excel sheets being taken onto your database. It's like that. So basically that is exactly how the concept of a relational database was actually put forth. We need a ledger to be sitting somewhere at a central place so that everyone can modify it. So that's how relational databases were started. Uh, what happens with this now once we have an architecture or once we have a data record which has rows and columns and all, what we need is how do we decide what or how do we decide the split of the columns, right? So that is where the concept of normal forms came into the picture. So you have some normal forms of databases like 1NF, 2NF, 3NF, and there are 4 and 5. With each step or with each increment of normal form, it basically reduces जो है वो data redundancy. So first normal form says every record has to be atomic, which implies that you should not be putting CSV values as part of your record cells, right? Because that's what 1NF dictates. If you would want to have that relationship, create a separate table and have it as different rows. So your rows have to be atomic. Oh, sorry, your cells have to be atomic with respect to its data representation. Then there is 2NF, and then the most common one is 3NF, which everyone uses. Right. So 3NF, if you don't know about this, go ahead and read it. Go read till 3NF only. So 3NF is something which suggests that every single thing should be separate out. So there should be zero data redundancy. So like for example, you should not have the same value being repeated at multiple places. Something similar to that we did with our tags. Like so in the last week when we were designing our blog, when we were talking about tags, in that what we did was instead of storing the tag name along with the blog, we assigned tag IDs to blog. So we had another mapping for blog ID and tag ID. Tag ID pe on the separate table we had this tag ID and tag name. The advantage of this is if we were to change something, let's say we want to change the name of a tag from ABC to PQR. So with this sort of indirection, so from one table to another, we just have to make change in one place and it will automatically get reflected in all other, right? So this is typically how a good SQL schema is designed, right? A good schema for relational database is designed. So this is very critical when you are not just preparing for interviews, but also when you're building system, when you're building the core crud of your system, you have to understand how would you reduce your data redundancy. That's the golden rule. If you can ensure that you have zero redundancy, it automatically becomes a good database design. But once you hit the scale, you cannot hit the scale with 3NF. You will introduce redundancy to make certain queries performant. We will look into a practical example later. But think about it. These are just guidelines. These are not mandates that you have to do this. Right. A typical example of relational database we all are quite familiar with is MySQL, Oracle, Postgres. Right. These databases have a lot of constraints on columns, combination of columns, foreign keys, composite keys, unique indexes, and whatnot. Right. So all of these constraints are important. Why? To drive transactions. Transactions are basically, transactions is the reason why people still prefer relational databases, because the transaction gives you asset properties: atomicity, consistency, durability, isolation. So what atomicity says is every transaction is a single unit of execution. So each transaction has like, now let's say you want to run 5 SQL commands, and if you enclose it in the transaction, what your database engine would ensure is either all of them are applied or none of them are applied. So due to any reason, if your database crashes in between, right? So that all the changes would automatically be discarded. So it's a single unit of execution, right? That's what atomicity is. Then your consistency, while thing implies that your database moves, or rather your data within your database moves from one consistent state to another consistent state. For example, you don't want the balance column of your table to be ever negative. You can add that as a constraint where you have something called as a check constraint. You can add it, and your database engine would raise exception or would raise an error when your constraint is broken, or when your update does not let your database satisfy that constraint. At that point, what would happen is your database would raise an error and it would not allow your update to go through. This would always ensure that your database remains in a consistent state. Why to that example of check constraint? Because that type of constraint is the least famous one, but the most essential one. Right. Other famous constraint are foreign key constraint. Like for example, if a certain ID refers to a certain row in that table, that row should be present. If that row is deleted, automatically delete all other rows which refer to that. Right. Some there might be use cases like this. So these are called on delete cascades. Right. So these are something that you should be reading about in case you don't know it. If you know it, it's a revision for you. Third thing is durability. So durability ensures that post commit, your changes are recoverable, which means even if your database crashes, once the changes are committed, they are flushed onto the disk. Once a database comes back up, the changes would remain as is. So even around the failures, your changes are not lost. Right? That's durability. So once the commit is done, your changes are recoverable. Right? Around failures of other transaction, around database failure, system failure, disk failure, whatever it would be, your changes have to be recoverable. But if your disk is like drilled and damaged, then the pura data loss. Then comes isolation. Isolation is really why your database exists. Like your isolation gives you concurrent execution. So multiple transactions running in parallel. So a great analogy of isolation is basically multi-threaded environment. So similar to how in operating system or while running your code, if you have multiple threads, you have to ensure that your variables which are being shared across threads are protected. So your critical section is protected. Something very similar to that, isolation ensures that multiple transactions being running or being executing on the database at the same time, they don't impact each other. And this is not something that database guarantees. Database gives you tools to ensure this happens. So these tools are nothing but logs. We'll talk about that. We'll talk about logs, transactions, and all of these things in detail. Right. So the first week was all about scratching the surface. Like we went into database, we picked SQL database, then no SQL for our discussion. We did delegation, deferreds, and all of those parts. Now it's time that we, instead of scratching the surface, we dig the surface and understand all of those things in detail. And we will have a very exhaustive discussions around it. So what I would really want you guys to do is implement or rather simulate transaction isolation. Like on your local machines, have one setup of MySQL Server or Postgres, pick your favorite relational database, have that server setup running, and then try to run transactions and see what happens when multiple transactions happen at the same time. You can explicitly make the transaction very long and see what happens when two very long transactions go on. Let two transactions update the same value. What happens then? Like how can you simulate that? I'll talk about it, how to do it the best way in the future part of the session. Right. Implement transactional durability. Handle system failure. So while a big transaction is running, try to kill your database server and see what happens. Right. I can give you the answer, but it's better if you discover it on your own, because you learn so many things about it once you are getting hands-on on that. Right. Then one very interesting that you can build, and it was and basically this is the question that I typically ask during when I'm interviewing someone. Okay, how will you build a trigger framework on top of a database? Like for example, if someone asks you to build something like basically whenever the age is 18, update a certain row which says like now I'm eligible to vote. Right. This is something, this trigger framework is typically given to you by your database. But if you were to build this as on the application side of things, how will you model the thing? So here the challenge is not about implementing it, but challenge is about designing key. How will you take input your where clauses? How will you take input key? What's the condition which when met, you would take a certain action? Like it's more about how will you structure your input, output, your low level code. Try to build this. So this is something that database gives you out of the box. You can configure your triggers, but try building it on your application side. So you might want to use something like an SQS queue where you are publishing the update, which then gets updated on the database and all, right? Something similar to that, but build a very generic trigger framework. That's a very interesting problem statement. You can start with a very small thing, max 50 triggers would be there, and then you can have your own. So this is where the main challenge comes on. So specify your own specification language. Okay, how will you specify or how will you define your input? When this condition met, what kind of conditions? How will you take this as an input? How can you model it on JSON? If you don't want to use JSON, how will you model it as a raw text? What kind of, or basically what kind of semantics would you use to understand the query or understand the condition, understand a complex condition, not just a single condition like A equal to B. Something as complex as A equal to B and B equal to C, but C is not equal to D, right? That's a Boolean expression. Something that has less than, greater than, some nested condition if you want to build something around it. So this is a very interesting problem statement that you can obviously work upon. Okay. And while doing all of this thing, you can skip using a SQL engine if you want to, and you can build a very simple in-memory hash table, use that as your database and build something around it. Right. So this is a very fun exercise that you can do. If you get time, please do that. I've built something on my own around it, and it has helped me understand a lot. It has helped me understand how to design a good input-output systems. Like how can we, or how should we model our systems to make it extensible to have any kind of inputs and generate any kind of output. That's why. Okay. Next part, database indexes. Indexes, the notion is very simple. Indexes are there to improve lookups. Like they have no other roles. Like indexes, the job of indexes is to make your lookups faster, right? It improves lookup performance. How? Because instead of the same reason why what we were discussing in the first pick and the first thing, that your row is quite big, it has to go through a lot of data to reach to that particular thing. Instead, if I create an index around it, I have fewer data to read and process, and I can have something like an inverted index. For example, I want to find all the rows having value equal to or having state is completed to be true, right? So I can just have mapping of is completed and then all the rows that it maps to, right? So indexes are there to improve lookup performance, but they come with a thing where it decreases the write performance of the system. Why? Because whenever your record is being updated in the main clustered index, jahan pe the actual table lies, that has to change. Along with that, synchronously the indexes needs to be updated. And because of this, what has happened is the one write that you make on the database, it fans out into multiple writes. Let's say one table has 5 indexes. So the every single write you perform on your table, it gets amplified into that one write plus 5 plus write on the 5 indexes. So it amplifies into 6 writes. So if you have large number of indexes, it also decreases your database performance. But when on the write, basically when you are writing something, so if your table grows big, if you are, let's say if you are hosted on AWS and you have a massive table, have massive indexes, then what you have to do, and if you're seeing a dip in performance, you might have to improve on write IOPS that you have, because now your IOPS per, basically the IO operations per second happening on the write have to be scaled up, right? So you need better disk to do that particular job so that you can have faster IOs, right? So you need higher IOPS when you have large set of indexes, right? So index of, in a very simple term, and basically this is exactly how most of the database actually implemented. It is nothing but a very small table having just 2 columns, where you have like your primary key or candidate key or anything that you would want to store. Like let's say you are storing is completed whose value is true or false or something. You would have 2 columns where all the unique values of that particular thing is listed. Let's say in this case for is completed, it would be true, false. So you would have one row for true, another row for false. And for that one row, you would have you'd map to the ID of the row, where you'd point to the ID of the row in the main clustered index. This way, it would become 2 hop lookup. First one, it would go to the index, get the row number. From that row number, it would go to that other index. From that row, it would get the actual row content. Right. So that's why index lookups are slow. Here, one interesting thing is you have 2 types of indexes. Primary index, you have a different type of index implementation. The main implementation what I would want to talk about is like your clustered index. So your main table, the way you are storing it is also stored as a clustered index. So this clustered index, what happens is, along with the value that you are storing as the key, for example, is completed true or false, instead of just storing in the reference key, which row ID does it belong to, it actually stores the entire row. So clustered, and on the other end, the primary index that you have, in which it has key and the address to the data. For example, true, and it points to the row where that particular data resides. So here you have to have multiple. So your primary indexes are leaner because they have to store very lesser data. You can load this very easily in memory and process it quickly. But what it does not do very well is it does not help you serve results faster as compared to clustered index. So with clustered index, you have the index and the data residing together, which means it does not have to go to the primary table to get the row ka data. It can directly serve it from the index itself. Right? So clustered indexes are really fast while serving the request. So it makes lookups even faster. But obviously, what happens is, although it boosts lookup performances, but writes become much costlier, because now any update that happens on any of the row, the clustered index with the entire row ka data also needs to be written. Right. So keeping clustered indexes in sync is very challenging. Challenging as in with respect to time and performance. So having a lot of clustered index is a bad choice. 3 per table on an average load of, let's say, 1000 requests per minute is nothing. Your database can very easily handle that, right? But having that clustered index, but you have to choose which index is your primary index, or the structure of that index is primary one, where it points to key and address to something, and where will you use clustered index, right? Because if you use clustered index really well, it can give you massive performance boost out of the box. So your SQL would very easily scale, right? On the other hand, for primary index, it becomes a one hop thing, right? Any questions till this stage? And obviously the data structure that we use to store table data and index data is exactly the same, the B plus tree. So the read about how B plus tree does serialization and how it internally stores it. It's you might have studied in a database system, but it's good to have that thing refreshed, because that's when you would appreciate why would you have to run defragmentation on your database? What would happen when, where, and how? Any questions till this point?
Yes, Arpit, I have one question.
Yeah, please.
I read it somewhere that most database engines like NoDB, they have write back cache enabled by default. So the queries are first written into the memory and then eventually they get flushed into the disk. So does it impact the application performance?
If your update first goes into memory, that's what you're saying?
Yes.
If your update first goes into the memory and then goes into the disk, that's a major problem, because if a database crashes before writing it to the disk, your changes are lost.
Yeah.
So that's usually tunable. They might make a commit log entry or something around that. But that might be true if you have read it on the official blog of MySQL.
No, I have not.
So we typically reconfigure the database to have it like write. We don't use cache. We just use cache for lookups to gain better performance for lookups and not for anything else. You should never be using, especially for transactional data, you should never be using a write back cache. But if your database does it along with commit logs and all, that's still okay.
Oh, thanks.
If you were to, let me just float a random question. If you were to implement clustered index, how would you do that?
Okay, here when you mean key, right? Is there any column that you have in the data, or?
Yeah, so let's take a concrete example around this. So let's say I have ID, name, age, address. Okay, and now what I want to do is let's create a clustered index on age. Okay. How will you represent this thing, or how will you implement this thing?
So here you will also have to have a key, right? Let's say ordered by name.
Why? I just want to create a clustered index on age.
So the index is created on age, but under the age, it's ordered.
By default, ordering is by ID.
Okay, got it.
So for the same age, if you have not specified any ordering criteria, it is by ID. So that's a great point. So that's exactly how everyone should think about it. Array, by what should I have my order? Because there would be a lot of conflicts over here, right? So think about that while designing, because this is extremely important when you move from SQL to NoSQL. So if you're doing that database migration and you are re-architecting your SQL models into NoSQL world, you would have to think about all of these decisions.
One understanding I have is, when it's a cluster index on age, does it mean index contains the index contains age, but what else is it containing along with it?
Varun, your voice is too echoing. We are unable to hear you clearly. Say something similar that happened on the first week. No, it's still worse. Just try to fix something if it's a little misconfiguration, because you might have a great thing to add here.
Yeah, I mean, so let's say the index contains age, but what else does it contain along with the age? I mean, from my understanding, clustered index is something that along with whenever you're doing some query, you get the result in the index itself.
Exactly. That's exactly what clustered index is, right? So if we were to implement clustered index, so let's say why are we talking about this is because let's say if you're building DynamoDB, right? So DynamoDB, if you were the founding member of Dynamo and you were trying to build a database like DynamoDB, in that case, DynamoDB's indexes are nothing but another DynamoDB tables, right? When you are building something as scalable as DynamoDB, it asks you when you're creating that index, which attributes do you want to project, right? So when you're creating index, it says that by default it is all attributes copied. So by default, DynamoDB creates clustered indexes as part of its implementation. But then you also have the choice that only index the attributes which are there is part of my index. So let's say if this was nothing but my but a new database which I was creating, let's say DynamoDB implementation. So there, if I create an index on it, so it asks me what all attributes do I want to project. So I can just say that I want to project just age along with ID, or I want to have age along with ID, name, and address. So these are design decisions that you have to take, right? This is why it is important. So when you are designing your own storage engine, or when you are modeling something on your own, right, at that point, these kind of decisions help you gain performance. Like for some use cases, let's say the kind of query you just want to run is count the number of people by age. This would be more than enough, right? But if you want you are querying people by age and you want to get all the details, this would give you a better performance, because then it does not have to do another lookup on the main table to get you that value, right? So one read does not fan out into two reads. If you have clustered index, it would be one read, that's it. But if it's a primary index sort of thing, so from age, so then from here what would happen is age say ID mila, and from ID it goes to this thing and gets me the rows out of it, right? So if you were to build that system, if you were to implement that system, every write that you'll make, it has to synchronously, this is a very important part, synchronously, it has to write or it has to update the indexes, right? So and worst part is, let's say you made an update on one part on your primary table, but your update to this index wala table failed. How will you roll back, right? You need to identify that, your application needs to understand that, right? This is very important when you are building a storage engine, right? You might not build it within first couple of years. If you're fortunate enough, you might build a storage engine in the first couple of years of experience. But then with time, when you are taking up bigger opportunities, bigger roles, this is something that will become a norm, where you are being forced to take such decisions on how do we implement that, because there are so many places where having this kind of thing or implementing this from scratch could go wrong, right? In your application code, your one write gets panned out to your writes to primary and your write to index. This failed, this passed, this passed, this failed, both failed, right? And how will you even, not getting safe. So this is something that you guys like always have to think about. Ki at every point, my program could fail. So I need to ensure my rollbacks are good enough. How do I do rollback? When do I commit? Once I know that everything is correct, then only I'll commit. So to get a deeper understanding of it, you need to understand DB internals, like how SQL engine does it. That's a great inspiration to have. The way SQL engine does it, it would help you make great decisions around it, right? When you're building your own storage engines and all, right? So keep that in mind. For some reason, my iPad stopped. Okay. Yeah, iPad का काम करने को नहीं चलता है. Unable to connect. What happened? Just give a minute. Something is wrong with
Your pencil may get discharged.
no, pencil is okay. It's 100% charged. My iPad is unable to connect to Zoom. एक मीटिंग में आ रहे हैं, ठीक है, बेटर, ठीक है, चलो. Now So try to model this thing. Why I'm saying this? Try to build this. So try to simulate this on a normal SQL database. Try to simulate this. Have one table for which stores your primary table. Create a separate table that for you acts as your clustered index, right? And see at every step when something fails, what happens? How will you prevent it? This is very important when you are building systems. This is very important when you are making, or basically when you are doing that kind of low level code, right? It's not just related to storage engines, but a lot of your application code also needs to ensure this works well. Yeah, Umar?
So like I've not worked with extensively with database. So I just had one question. So create an index. So do you need to specify to the application that only consume the data from the index, or the database does it automatically?
The database does it automatically. But if you're building DynamoDB, if you're using something like DynamoDB, or so like SQL databases, traditional SQL databases like MySQL, Postgres, they do it automatically. But for a NoSQL database like DynamoDB, you have to specify that go read from this index, go read from this index. So you have to use that particular index because indexes are also tables for
Right.
DynamoDB.
So basically, like if I'm using MySQL, I do not need to specify on the application side of things that you
Yes, you don't need to specify. The database engine will make that intelligence choice, would see your query, would see that, okay, you are fetching this attributes, your where clause is on attribute A and B. What's the best strategy for me? On which index should I pick first? And then go through the main table if needed, right? So that would be something that would be taken care by your database engine.
Got it.
That's why it uses an imperative language, right? Because the optimizer is very good of,
yes,
I think.
Yes. So with SQL language, you never have to specify from where you have to read it. You just specify what you need it, what kind of things you would want to filter it out on, but you don't specify how to do it.
Okay.
Right? So how all part is taken care by the engine.
So these decisions are mostly around like who designs the schema and
designs the schema. Yeah.
And administrators also do, like handles these kind of.
If you have a big company, administrators and all, then they will help you do it.
Okay, got it.
But as an engineer, you should definitely understand how to pick those things, like which index, when, where, how, and why.
Got it.
Okay. Yeah, Chandan.
Yeah, good. So like when last week you talked about the replication of the database, right? Like master slave architecture. On top of that, we are implementing the indexing. So if any write is happening, so and then all the slave databases, they need to be synced with the master one. So in that case, these indexes also get synced at that time on the fly we do, or the later.
No. Okay. So one way for the one way that replication happens is, let's say you have fired a query. So the way replication, basically this is a great question. That's why I'll be going in a little deep in a little depth about it, because it would help you understand it would help you all understand a lot of stuff about replication. So how exactly the replication is implemented. So let's say you have a master database, okay, on your master, and you have, let's say, 2 replicas set up from here, replica 1, replica 2. One replication strategy is very simple. What it does is, any query fired on the master, the same query gets fired on the replica, both the replicas. So let's say you do a create table, or you do a create table, create index, whatnot. The same query would be fired on both the replicas. Right, so your query being fired on the master, it got committed, the query being sent to replicas independently, and those queries being run on the replicas. So your replicas are actually running the same query as your master. Okay, so let's say you created an index on master, that same create index command would go ahead and run on both the replicas. So that same index would be created there. Now let's say you insert something on your master. So you did insert into this table, do insert XYZ. The same insert command would run on both the replicas. Now that replica it's also standalone database instance. So when the insert runs in, it does that exact same thing. It updates the main table. If there are any indexes, goes ahead and updates the index. So there is no differentiation, right? So it's just about the queries that go to the replica are same as the query that runs on the master. But these are all update queries. Basically, anything that updates the database, its data, its index, its definition, whatever. Right. So through this, there is no differentiation between the two. So since index exists on both master as well as replica, we have insert command, the kind of actions it would do on the master, the same kind of actions it would do on the replica.
Okay, and if I were to create a new index on the master after having the replicas, then in that case also will it work like that?
Anything that runs on the master goes, it will get reflected onto replicas.
Okay, yeah.
Right. This is one kind of replication strategy where actual SQL queries are executed on replica. There is another kind of replication strategy where only the changes are streamed to the replica. Like for example, I've inserted this row. So go ahead and update and make these changes. So, but people always choose a SQL query application because it is much more consistent. The other strategy is optimal, but the first one is very consistent. It gives you fair bit of exposure on what's going to happen, and if something bad goes, if basically something goes bad, it is easy to recover. So almost every single database out of the box is configured to stream out queries and not the data across, because data can be huge. Queries are very lean. Yeah. Okay. Yeah, Anshul.
Yeah, so I wanted to ask like how the clustered index are fast. Like, are they stored in B plus tree or?
Both the indexes are stored in B plus tree. Clustered index are fast because it, like, if you have primary index, that's what I said. If you have primary
Don't
index,
have a double lookup, right?
bus. So clustered index may the data itself is stored in the index. The entire data, the entire row data is stored in the index.
So internally they are not stored in table, but in B plus tree, just for
Table bhi hai na. Basically, table is also what? A B plus tree.
Okay.
Your table is a B plus tree. Your index is also a B plus tree. Okay. But in the B plus tree, when the information is stored along with the index key value, let's say if you're creating an index on age, along with the age, it would also store the entire row data with it. So when you're making a query, it does not have to go to the main table to get the data, because data is stored along with the index.
Got it.
Right. So एक साथ it ships everything. Okay. Chal. One final question before we move to the next one. Yeah, Prabhat.
When we create B plus D, is data stored only in the leaf nodes, or like we have data?
B plus D is it's stored only on the leaf node, na? That's exactly how. So there is no special alteration to any B plus strategy. It's exactly the same.
Okay, and like I would like to add one thing, like in MySQL also, like we can give sometimes, like in some cases, some suggestions to the engine, like for using indexes in like some cases, if we are sure like that it will help.
Yeah, definitely. Great point brought up, Prabhat. We can specify, we can, in the SQL query, we can specify use a certain thing. So you can give it use this index to run this part. So sometimes for some queries, it's a very rare thing, but for some queries, the kind of execution path a database engine takes might not be optimal with respect to your use case. It is quite possible, right? So always understand the execution plan. What you have to look for is the execution plan of your so what you have to look for is the execution plan of your system, or sorry, of your query. Whenever you are firing it on your database, you can see the execution plan of your query. So go through the execution plan and you will see, so you can use it using the explain command, right? Once you do that, you will get a very nice output which says that what all indexes will it use, what's the cadency of it, and how it would execute. So once you have that information, you can choose to use a certain index or not, or if you want to change something.
And like one more question I have, like on this replication strategy, suppose we send the query to the replica, like on the master itself, like we when we get the query, we create a query plan, right? So like isn't it inefficient to just send the query? Shouldn't we also send the query plan to the replica so that we do work
internally it might be sending. I don't know those part of internals, but it's easier to understand the query is executed there.
Got it.
So obviously it might be doing that optimization. I'm not denying that, but that's definitely that I'm not 100% sure. No, that's why I would not want to comment on that. Achha, it's connected to different Wi-Fi. That's why it's not working. Wait, sorry. That's why it's not working then. आप चलेगा ना? I'll just reconnect this. That's why I thought why it was lacking a little bit. Yes. Fine. Chalo. Happy. अब पास चलेगा. Next up is database locking. This is the most important part. Most of the folks, most of the people I've interviewed or I know of, they don't know about this thing. Right? This is very important when you're designing great systems, like locking. So your and this locking is not really very specific to SQL. We will look into the context of SQL and NoSQL, but for now we will just put our focus on SQL. And you see any company out there, you see any product out there, the way they do things is by using locking strategy, because locking is something through which you get isolation. When you build system which is heavily concurrent, like Hotstar, Dream11, Xiaomi Flash Sale and whatnot, you'll have to understand locking in depth. Right? Locking is very similar to mutexes and semaphores. You're just trying to protect your critical section. Right? Something very similar to that. You're just trying to protect your data by applying locks. So there are two types of locks: read lock or shared lock, and write lock or exclusive lock. So read lock, what it does is it reserves the rows for read for your current transaction. Other sessions can read the log data. So with the read lock, other transactions are allowed to read the data, but they are not allowed to make an update to it. Okay, so other transactions, once a certain transaction has taken a read lock, other transactions won't be able to update the data. With write lock, once a session has logged a certain row for write, other transactions cannot even read the data. Basically, let alone write, they cannot even read the log data, right? So if you see, read lock is very lenient as compared to write lock, but if you have taken a lot of exclusive lock or write lock, it would obviously hamper the performance of a system, because then it is making things exactly sequential. Like once I've taken a write lock, I'll not allow anyone else to even read the data, right? So you need to keep that in mind while you are taking this lock, right? How will you take this lock? We'll discuss it. Well, let's talk about log granularity for some time. So log granularity is on what all things are logs taken. Logs are taken on table. The entire table could be locked. Like your query might be bad and it might take a lock on entire table. You can take locks on certain rows. You can also take locks on certain columns. And there is a very interesting page level locking as well. So a certain page on your database, so since it's B plus trees, everything is page, that one page can be locked. If you have not created right set of indexes, by default, the entire page is locked, right? So if the engine, so once you have taken locks, obviously what comes with locks is deadlock. So let's say transaction A wants lock on row 1 and transaction B wants lock on row 2, but transaction A holds a lock on row 2 while transaction B holds a lock on row 1, right? This is a classical case of a deadlock where both the transactions are locked in the certain state. So what database engine does is, whenever it internally is asked to take a lock, if it detects a deadlock, it kills the transaction. Okay, it kills the transaction, but which transaction? It does not kill both the transaction. It kills a transaction that has detected the deadlock. Let's say my second transaction is what I was running which resulted into a deadlock, it would just kill my second transaction. My first transaction would continue to run. Right. So this is very important to understand. When you're building systems at scale, when you're using SQL databases at scale, this is what is the differentiator that would make or break your product. Right. So what do you need? Why do we need DB logs when we can handle this on the application side? Because if you do it on the recently I posted on LinkedIn about isolation, and some folk commented all of this use case can be done using distributed logs. But if you use distributed logs, those are very, very, very costly, because distributed logs matlab you are taking logs over network. So many things could go wrong. Distributed logs are reality. People use it a lot. But when your SQL table gives you all of those options, you should leverage that. It's much faster, much reliable than distributed logs, right? So with distributed architecture, locking and all, you know, when you have multiple things, here what we are seeking is when the multiple transactions are running over this, you can take application level logs using Redis and all. That would make things terribly slow. Don't ever do that if you can do it well on the SQL side, because your database is there to ensure consistency, right? It's a job, right? Now comes the most interesting part. How do you actually take logs on the system, on the rows and all, right? So let's say when you want to take logs on reads, what you do is if you query the data and then insert an update with the same transaction. So what you do is remember to set your auto commit to false. By default, whenever you start your session, the auto commit flag is set to true, which means every line is basically committed. Every line is an isolated transaction. So if you're mimicking something like this, set auto commit to false, and then you can mimic a transaction using begin transaction and end transaction. So now what you do is, I'll share how to take read logs. So you would write your select statement like usual, select ABC from PQR. At the end, just add for share. It implies that for shared log, I want to, so all the rows which are selected by this query, by this clause, will be taken. You'll be taking a read log, or you'll be taking a shared log on those, on the output of that SQL query, on the output of that select query. So the final computed result set is something that you will be taking a read log on. So shared mode logs on any row that are read. Other sessions can read these rows, but they cannot modify. If the rows are modified, other transaction will wait until the first one ends and then use the latest value. So if you have two transactions, one transaction has read log while other is trying to read and also modify, it would have to wait until my first transaction is complete. This is something that you should definitely try out on your local machine. Definitely go and spin up MySQL server, set auto commit to false. This is where I've written set auto commit to false, and mimic this behavior. You will learn a lot about database locking and where you can actually use it. So start one transaction that takes read log on certain number of rows, start another transaction that reads the rows, and then it tries to update something. You would see that session is just waiting for the first transaction to complete. Once you do a commit or a rollback on the first transaction, then it goes through. Right. This is how it is done. Now, how would you take an exclusive lock on it? Is instead of using for share, you would change it to for update. Once you use for update, it would take an exclusive lock on the same rows that are part of your result set of your select query. So it locks the rows and any associated index. This is very important. It locks the rows, not only the rows, but also the associated index entries, which means if you're taking an exclusive lock, the data which you can explicitly specifically read from the index, that is also locked. So your reads from the indexes are also blocked, which means your select queries which are being optimized to read it from indexes, they are also blocked from reading those entries. So no one is allowed to read the entries which have an exclusive lock by a certain transaction. So other transactions are blocked from updating these rows or even reading them, right? You can also configure this using isolation levels. Read about isolation levels of your databases. So there is isolation level like read committed, read uncommitted, serializable. Read about them, right? What happens, and obviously all of these parameters are tunable. You can tune your database with for the best of your use cases. Right. It is okay. One very interesting part. So now here what we talked about was locking the rows. Now what if it is okay? Like let's say, what if it is okay to skip locked rows? Right. So there are rows which are locked by a certain transaction. And now let's say when other transaction comes in and the other transaction should not see the rows that are locked. What if I have this kind of use case? Give me one example. Give me one example where this can be handy. Where it is okay for a certain transaction to skip the rows which are locked and move to the next one.
Seat booking, session booking. Like
Session
book my
booking.
show.
Perfect. Book my show, right? That's a great example for this. So the seats that are locked by certain people who are about to make payments, you can still see the seats that are blocked, but you should be allowed to book other rows, right? So when you're booking tickets, so if you're building any system that deals with ticket booking, you can also model SQS queues kind of thing, or a simple message broker on SQL table using this, where a certain rows are locked, but you can move to the next row. Right? You can build ticketing server using this. So anywhere where you want to simulate something like ticketing thing, where you have certain rows locked, but you can skip that and move to the next one, that point you have this very use case. So now what happens is, if it is okay for you to skip rows, there are two ways to do it. First is no wait, which implies that locking read never waits to acquire a new lock. Query executes immediately if the row is locked, which means it does not give you an error. It says it's okay for me to skip the locked rows, but I would not want to wait. So I don't want to wait on any row which is locked, and I want to kill myself. So I just want to kill the transaction. I just want to basically I just want to carry on with this. Right. So let's say I have to select star from T where I equal to 2 for update, no wait, which means I'm trying to read row where I is equal to 2, and I don't want to wait. So if the row is locked, I don't want to continue at all. Right. Another one is skip locked. So, and basically the above query is the exact query that you would fire. So select star from T where I equal to 2 for update, which means you want to take an exclusive lock, but with no wait. So if this row is already locked, I don't want to do anything. Just let me continue. Second is skip lock, where it removes the locked rows from the result set. So once it computes the result set, it sees that, okay, these are the rows which are locked. And if you're given skip lock, it would skip those rows, and then it would give you the other rows which are, and obviously then you own the lock on them. So with this statement, where you say select star from T where I equal to 2 for update, skip lock, which means if there were any rows that had I equal to 2 which are already locked, skip them, give me other ones. Right? So it would still match that I equal to 2, and it would skip the rows which are locked. Both of these use cases are both of these constructs are very interesting, because it helps you build systems that you always admire. Like, how will you build a ticket booking system? How will you build, or how will you use SQL storage as your message broker if you want to use it? How will you build your own SQS? Right? If you have such things, you can always leverage this. How will you build a flash sale? We'll use this. We will discuss flash sale in detail once we cover distributed systems as well, because there are 5 different ways to model flash sales. We will cover that part later. But think about so many use cases you can build using just raw SQL table and using the standard language constructs, right? So next time, if you are discussing ticket booking, flight booking, or general ticket engines, message brokers, Kafkas, you can build Kafkas using SQL storage like this. Like basically, these are the tools that you have to use using database locking, read lock, exclusive lock, and ability to skip the locked rows, or to either kill itself or just skip the rows that are locked. Right. These 4 becomes the main powerhouse that would help you, build great systems on top of SQL databases. And why so I'm adamant on SQL? Because SQL gives you ACID properties. Your NoSQL does not give you ACID property, or does not give you efficient ACID implementations. Right. So that's what I want you, please do this. I learned a lot while I was experimenting. Theory is okay. Once you are getting hands-on, you'll understand things in a lot more depth. I have everything that I would want you guys to know before you jump into this. Set auto commit to off is very important. and then experiment with this. Play with read logs, transactions, deadlocks, simulate the scenarios. See what happens when the transactions are in deadlock. I said that second transaction or the transaction which detected gets killed. Try that out. Understand how that functions. Effect of skip locked and no wait. See what kind of things you get as an output. Where can you use it? Try to model systems like Book My Show ticket booking or Paytm Movies ticket booking or MI Splash Sale using this, right? So what happens to a row after acquiring the lock and then value getting modified, right? So once you have acquired a read lock and the value get modified by someone else, what would happen, right? Find situations where you can apply these things, right? So I just gave you, 4 or 5 applications. Think about 4. Almost all the systems that you see out there which are dealing at scale has to use locking. Dream 11 joining a team has to heavily use locking systems. Zerodha has to use locking systems when you are booking that, basically when you are actually buying that stock, right? Because there are so many transactions going there at the same time, right? You have to have that system. Okay. So let me take a few questions. Srisha.
Hey, so what I was trying to understand is, let's say you have um, a lot of a very high throughput booking, right? Ticket booking. And let's say you have a SQL server and you have a Mongo server, and let's say 50% of the transactions are going to SQL and 50% of them are going to Mongo. And in front of Mongo, you have like what do you say, some sort of a locking mechanism, like let's say Redis or some etcd cluster
It's a
or
very
something like
complicated
that.
architecture, but yeah.
No, so what I'm trying to understand is if you can sort of figure out how these 50% transactions going to Mongo behave and 50% going to SQL behave, what would be better? Would Mongo scale better or would SQL scale better with your external locking thing?
SQL would anyway be better because see anything that you can do with Mongo, you can definitely do with SQL. Right. Mongo just gives you ability to shard well. Right. The kind of ACID guarantees that Mongo gives you is across shards and it is extremely slow.
Okay. And what happens if you can sort of write your own logic on top of that? Because
handling
you
it
can
on the
expand
application
and you
side using
decrease your
remote
shard,
locks.
right?
So basically handling locking on the application side, right? If you do it on the application side, then you would have to use remote locks.
So you mean like there is a you mean like there is some external server like Redis or something where you store those locks?
Yeah. So a lock manager to store those locks.
And and as the scale increases, handling infra in terms of SQL and Mongo, which would be better? Because I've not done this before, but
SQL.
Okay.
See, MongoDB is okay. MongoDB is okay. You can use it, but you need to understand when to use it. So MongoDB pay if your system needs transactions, if your system needs consistency, if your system demands acidity, right? You'd have to use SQL database. You can hack your way around. You can hack your way around using NoSQL. Like for example, for cost purposes, let me use DynamoDB for some time or MongoDB for some time because free hosting is available. But if you're dealing it at scale with transactional data, especially payments information, or you need very high concurrency, SQL would do a far better job than a NoSQL. Because all the data would reside in one place, you need consistency, you don't want data to be corrupted. NoSQL, there is always a chance of data being corrupt unless you take remote locks, and remote locks are very expensive.
Expensive, okay.
Expensive with respect to time, obviously. But if your database is anyway sharded, then it's okay. Because sharded database, you can do a lot of fancy stuff. So sharded database, but if you're sharded database, you can also shard SQL database system.
Okay, is SQL easy to shard and scale as much as
MongoDB is easy to shard. MongoDB, Cassandra are meant for sharding. SQL is not that easy to shard because then we will talk about that architecture. When you shard the database, your query is anyway being fired onto just one of your database. So all the data within that should reside within that database. You can't have a cross database joins. You can still have cross database joins, but it will be very expensive. You can't have cross database consistency constraints. So those are challenges with sharded SQL. So there is a project called MySQL Vitis, VITSSE something. Go ahead and look that. They have sharded MySQL offering.
Okay, got it.
We will discuss a lot of this chunk in detail in the future section where we talk about remote locks during the next week on how do we use it, when do we use it, how do we use it with SQL and all. We will have a very in-depth conversation about it. So, yeah, Ronak?
So Arpit, what I understand from no wait and skip lock is, let's say we have a table with ID equal to 1 to 50 and we have applied a lock on modulo 2. Let's say even numbers, we have applied a lock. So if I apply no wait, so the transaction will fail if I want to update the even numbers.
It would not find any rows. Basically, it would not find any rows there because they are locked. So it says that I would not want to block. So we have seen a lot of places where my transaction waits until other transaction actually releases the lock. But what if you don't want to wait for other transaction to release? If you could not find something which is free, then you just terminate it.
Okay, so that the transaction will fail in short.
Not really fail, but it would not find anything. So you can have this under another transaction. And now let's say if you could not find anything here, you would want to do something else, right? So your SQL statement would not fail. It would not lead your entire transaction to fail. It would not do a rollback. It would just continue. So think about this as no wait is trying to remove the rows which are there. It just says that I just don't want to wait for the lock to be released.
Right. And skip log will just update the odd number rows.
Yeah. It would just skip which is locked and then no. So this would only happen when your other transaction the kind of update that you wrote is basically updating all the rows. I'm assuming that, right? If it's updating all the rows, then even ones are locked. So then odd ones will be updated.
Right, and even will be skipped.
Even will be skipped. Yes.
So the main use case of no wait is in procedure when you write a begin transaction and end transaction, and you have to you have many sequels and you can just skip one of the sequel. That's the use case of no wait.
Yeah. So mostly skip locked is something that is very heavily used. No wait is still people usually don't use it, but skip locked is something that is very heavily used. Okay. Yeah, Anshul.
So what will happen if no wait is having 5 entries in result, but one of the entries is locked? Will the 4 rows will be returned or no?
Check that out. Check that out. What happens? You will discover something very interesting that happens. See, I can give you an answer, but I want you to try that out because these kind of use cases actually, once you have a hands-on understanding of this, now you will make far better decisions than if I tell you right now. That's why. If you anyway want to discuss it, I'm always there. I can anyway help you with that. Yeah, Branshu.
Arpit, so my question is little different from this. Actually, so the tweet or text kind of a system, are they considered transactions? For example, WhatsApp or Twitter.
No, they are not. They are not transactional systems.
Okay. So how does that work? Like when you have a write heavy and read heavy kind of a system.
Read heavy, write
for
heavy
example,
systems is okay to classify such things. So you would not want to have so typically transactional systems are those in which you need very high consistency at scale. So you have a lot of foreign key constraints. You have a lot of constraints that goes across tables, a lot of checks, and that too on a very heavy concurrent throughput, right? So on a very high throughput, when you're doing these things, those become transactional systems. You are heavily utilizing your SQL transactions where your transactions are big enough. For example, payment system, right? So your transactions are typically big enough because it has to wait for a lot of things to happen. It goes across systems to do something, right? So those are transaction systems. On the other hand, your messaging one is something that is just write heavy system because it does not need. It's just basically making one entry in your database.
Understood. So let's say, for instance, somebody is writing a tweet and update it in real time, right? And that gets kind of fan out for all the readers or followers. That is not considered as a transaction.
So transaction system is just typically with respect to that one API call under that one query. That's it. That's what is a transactional system. With this, although you might use transactions, but is your transaction waiting? Once I've made that tweet, it goes and sends out to all the things, and then my transaction ends? No. Because that is an asynchronous job where once you have made a tweet, it basically goes to all the followers. That's an asynchronous system.
That's
Using
eventual
delegation.
consistency, right?
That's eventually consistent, kind of eventually consistent if you are adding it into their feed. That's an eventually consistent system. Vishal?
Yeah, so on the ticketing system, right? So I've seen that when the payment fails, the tickets are somewhat blocked for some time and then they get released.
Yeah.
So the locking system, what it remains there for some time and then some query is fired just to unlock them or what?
How will you design it? So, Vishal, let's talk about this after 6th week. Then you will have a very detailed answer about this. Abhito, it is basically just the beginning, right? But it definitely uses SQL transactions. It definitely uses NoWait and all blocking time. But the way they are managing the lock period would be a little different. But there are a lot more things that we can cover before we design a great ticketing system like this.
Okay, fine.
It's a little too early to discuss this. That's right.
Fine.
Okay. Chalo. It's 5:07. Let's take a quick 5 minutes break. Let's catch up at 5:15 again. Almost 7-8 minutes break. So 5:15 we'll start, and then we'll talk about scaling relational database, and then we'll design a key value store on top of SQL database. Right. So scaling relational database, and then we design a SQL backed key value store. Right. This is something we'll be discussing after this. Chalo. Awesome. See you guys at 5:15.
Arpit, are you there? I have a small question.
You use a Dell. Okay. Varun is asking. So index is stored both in disk and memory. Yes. So it's not stored in memory, but it is cached in memory, depending on how the execution happens. We'll come into it how to gain great performance out of SQL storages and what's the importance of indexes.
Hey Arpit, so in the clustered index, so whenever you have, let's say 93, 94, 95, and let's say each of these have a pointer to some let's say 100 records, right?
Clustered index,
And
there is no pointer to 100. So all 100 records, so it's arranged. So your clustered index is arranged such that your query happens on that 93 and then it gives 100 rows. So that 100 rows are stored there, not the IDs of those rows, but the 100 rows are stored there.
Okay, so all the rows from the disk are pulled into memory, and then your application uses
memory pin no. Clustered index is also disk based, no? So rows are copied when you create an index.
Okay, got it. And then in those 100 rows, how is it arranged? How is it sorted?
By ID, by default, if you have not specified any composite parameter with it.
Okay, and
typically,
when you access
typically when you create an index, you specify the index on column A, column B, column C. Okay, so then it would first be sorted by column A, then by column B, and then by column C.
Okay, and when you say, let's say where ID equal to 93, now this access will be super fast. But when you put a condition on it saying some range query, let's say, and in those sorted rows, that range, how does it
would
walk?
go into
How
that.
does
It would anyway have to do that. When you apply range query, it would anyway have to do that. So basically, one is pointed query, which is lightning fast, and then comes range query, because then the range query. So here the binary search wala thing actually comes in very handy, where it basically quickly identifies the start point and then it applies that range where this starts from this to this. So since it is kept sorted, it leverages sorting. It basically leverages that indexes are always sorted by some parameter, and on that sorting criteria, it basically in the login time, it actually quickly matches those entries and then basically fetches you the result.
Okay, and can you add an index to those set of rows as well, or is it just sorting that we get?
It's just sorting that you get on a cluster index, but you can always create another index on any row, on any column that you want.
Okay.
Yeah, Rana?
So Arpit, in memory, like we won't store any index because let's say our CPU goes down, like our RAM goes down, like. But in this disk space, you will always get the index. So
yes.
What is
Indexes are always disk based. Indexes
Yes.
are always disk based. For databases, persistence is very important, right?
Exactly.
So indexes are always disk based. Indexes and the core data, everything is disk based.
Yes.
Memory is just pure caching.
Exactly.
So whenever it accesses something from the disk, it basically adds it to the in-memory cache and then serves it next time. If it makes a query, if the page already exists on the memory, it serves it from that. Right. So it might cache the data upon request, but it is not using memory as a primary source of the data.
Yeah.
Okay. Sure. Now comes a very interesting part, scaling relational databases. Like, so everyone says database, relational database, how do we scale? How do we scale? First week we saw, but let's thoda sa deep mein. So single database is single point of failure. It's not scalable beyond a certain limit because vertical scaling you can go until a certain stage. Now what would happen is once you're getting too many writes, you add read replicas to it. Right. So what you do is you just think about how they have come up with solution. It's not about understanding the solution. It's about how they have defined a solution, the approach. This is very important. This would help you design great systems, right? You need to don't go through the scene as is, like read between the lines. What would happen is if you have one database, it's taking reads, it's taking writes, a lot of queries are going there. Now, if you'd want to create something around this and scale this thing, you want to have two databases. But now these two databases, what's more important for you? It's always writes which are important, because writes say then you have more data coming in. If you have more data coming in, you have more business. So what they did was they thought about this. Let's just have one database for write, and let's create another database that can serve reads. The first database can also serve reads, but now that I cannot scale my reads and writes both going to it, and I know that my reads are 99%, but my writes is just 1%. So if I just have one database that handles only writes, then I'm directly shedding my traffic by 99, right? Basically by a factor of 99. So I'll be able to scale my database a little longer. I'm still yet to hit the limit. That's where the concept of read replicas came into the picture. So now my one database will take in all the writes, while other database takes in all the reads. Now, if I have one read replica, I can have multiple read replicas. Once I have multiple read replicas, I can serve more reads, because now typically my read replicas, they don't really have to care about locks, right? Because writes are not happening. I can have as many read locks as needed, right? And my read replicas can scale independently. And my master pay, which takes in the write, I have bought some time till my database hits that limit, right? This kind of strategy is something which works on intuition. So when you're designing in a system, think about this. How can you defer hitting the cap? So let's say your system has a certain cap. This is where I basically beyond this limit I cannot scale. What would be your intuition? This is typical example of divide and conquer. You are dividing your traffic into read traffic and write traffic, scaling writes, and you have basically bought some time around it, right? By just allowing writes to go on that one database and other databases to take on all the reads, right? The concern here is, what if your replica has to be always in sync. We saw how replication happens. Like what happens when master goes down? What would you do? Once the master goes down, either your replica takes in the place of your master. This is a typical distributed problem, right? Once one of your master goes down, another one takes its place. Typically in the cloud-based environment, there are failover systems. There are standby machines which takes in that place, right? So through this, what would happen is once a master goes down, there might be another standby machine. So one of the system identifies master is down, then another machine takes its place. Which one? It's a standby machine, which is just a read replica, not serving any traffic, taking its place. Or if you don't have any such system, you'd go ahead and click on 3 buttons on AWS and get your machine up and running. So you might have that big of a downtime. There will be massive data loss happening between that. So if you cannot bear even a single entry ka data loss in your system, let's say you have built a portal for GST, right? People are filing GSTs. You are driving India's taxes, right? If you're driving that, you can't even bear even a single write failing, because it would make everything go haywire. Given this situation, what you would have is you would have a standby machine, and you'll put that once a master goes down, like within seconds, your standby machine will take the place of a master, which implies that your standby machine should be as close to master as possible with respect to data, right? Any write that happens on master, like almost synchronously goes into that replica, right? These are basically storage redundancy practices, right? If you Google about storage redundancy, you will find some literature around it. But think about all the ways you can make the system reliant, like having a synchronous write, asynchronous write, how to deal with this. So if master goes down, what's your strategy? So these are typically DR strategies, basically disaster recovery strategies. So master going down is a disaster. What would be your strategy to recover it, right? Worst part, if your replica is in a different region, then though it takes even longer time for your data to get in sync. So you'll have higher replica lag, right? There are challenges, but this is how you can scale your database. So adding more read replicas is one way to scale your database, because reads you can serve independently than writes. Another example is what? Data sharding. So data sharding, what would you do? You would have multiple masters, but no data being shared between them. If you closely see here, I have two masters. Both are taking writes. Let's say a great example of this is stock exchange. Any transaction that happens on stocks happens on a certain company. Let's say Microsoft, Tesla, or something. It happens on that one item. Right, so you can very easily shard your system. You can easily shard your system such that all the stocks from A to M goes to this master, all the stocks from M to Z goes to this master, and each of this master has its own set of read replicas to follow upon to scale up reads. Right. So if you were to design your own stock exchange, and when your architecture like this is becoming a bottleneck, after adding read replica, you still need more thing. You'll go for range partitioning. Right. Here, what I've done is I've range partitioned my data such that A to M goes in one place, M to Z goes in other place. And each one of them is a setup similar to master replica, because reads definitely need to scale. But now I'm just responsible for a part of my data set. Now, if I'm seeing a lot more traffic from A to M, let me split it accordingly. Right. So I can continuously create a tree of databases. Right. That serves my ecosystem. Okay. This is data sharding. And this is only possible when my data is shardable. If my data is not shardable, which means I need cross database joins, I need cross database consistency requirements. No, that is not possible. That is not going to happen, right? If you have a use case where you can shard the system, that's when you can have sharding. Cross database joins are very expensive and almost needs to handle on the application side. It takes a lot of time to do those things and not recommended. Right? Go for sharding. Then the third and a little more advanced thing is having a multi-master setup. So the first one this one that we saw was having multiple masters, but data being totally mutually exclusive, right? But with multi-master setup, both are acting masters and both can share the data. So write can go to any of the master. So this architecture is not recommended. Not a lot of companies use it, but after a certain stage, you'd have to, use that. You'd be left with no other option to do this. It's a really complicated one because your data conflicts would happen. Like just imagine ID generation, right? Something that we discussed last week. So ID generation itself, if both database independently are generating IDs, then there will be definitely data conflicts. So then how would this conflicts be resolved? Right? How will you? So because it's a database, you can't manually go ahead and resolve the conflicts. You can ask your users to do it for you if there are any conflicts, but typically you would not want to do that. So this is a little complicated, but there is no way to do so. Specifically when you're doing data migrations, you might temporarily have a multi-master setup where writes can go anywhere. But typically what you do is you handle conflicts on your application side. You would never hear me out. You will never let your database have a conflict. Then you can have a multi-master setup. Okay. Understand this. You are not allowing your database to have conflicts when you're having a multi-master setup. This you can ensure on the application side, depending on the use case that you have at hand. So typically when you're migrating out of SQL into NoSQL or having a multi-region replication or some architecture like this, you would fall into this trap of having a multi-master setup. And that's where you would have to ensure that you are not letting your database enter into a conflicted zone. Okay, clear? Let me take the question. Yeah, Srisha.
Hey, could you go back to that slide?
Yeah.
Sorry. A little bit up, splitting data horizontally. Okay, so what I mean to say is, let's say you have 3 shards and your data is basically split into those 3, right? And if your data keeps increasing, each of the shards will have a higher number of writes reaching them.
Yes.
So now if you add one more shard, you'll have to reshard the entire system.
Yes.
Okay, and let's say you mentioned that there is this multi-master, setup, which what can it do exactly? It can add one replica for the master, is it? Or
no.
There will be one more
There
master.
will be two masters. It's like basically classical split brain problem. You have two masters. Write can go to any one of them.
So in a single shard, you'll have two masters.
Not in a single. It's so basically multi-master is not an extension of this. Think about multi-master.
Okay.
Multi-master is an extension of this. So instead of having master replica, you have master. You're right. So you will be load balancing across that master. So some query going to this master, some query going to other master.
Okay, got it.
See, after a certain stage, you won't be able to take in more writes. That's when you would have to have another master in place.
Got it.
So
we can use pre-sharding. We can use pre-sharding to prevent, like, if you anticipate later on the data will get go bigger and bigger. We can use pre-sharding.
Exactly. Yeah. If you have that foresight, your data will become a problem. Then you can obviously pre-shard your data accordingly. Yeah, Varun?
I mean, how do these big companies actually handle the data loss when there is let's say there is a single master setup and there is replica lag, and obviously the replica takes over, but whatever the replication lag is there,
data is lost. Yeah, you can't do much. Unless you are logging all the requests. You can't replay it. If you have something like a replay logs or something, if you have logged all the requests that you have and you would want to replay it, but that's even bad, because if your master was down, then your API would have anyway thrown a 500 to the user. Right? Would you want to go back and apply the changes without your end user being aware of it? Right?
Okay, I understand.
Right? So think about from the perspective of end user. Yeah.
Okay, so I just wanted to add one thing. So this is through a blog I read way before. I'm not sure how accurate it is. So whenever you get a write to a master, it first writes it to some append log and then adds it to its index parallelly. Like the first thing it does is like writes it to an append log, because while it's adding to the index, if the master fails, then once it comes back up, it can rebuild its indexes using that append log.
That happens only when when you're within that transaction. These are ways to handle transactions. Right. So not everything. So it's not you should, if you have given 500 to the user, which implies that the request was not fulfilled. Right. Would you go back and apply those changes without even him or her knowing about it? So typically data loss is data loss. And actually that's a much better way to handle it versus automatically trying to fix the situation.
Arpit, let's say we said that the request is successful to the user and the write happened in the master, and after that, and without the replica getting the changes, the master went down. So that data loss is basically acceptable.
No, then see the master went down, but the disk is still there.
Okay.
Did your disk also crash?
No, once it comes back,
there,
yeah.
Once your database restarts, it would still read the data, and then your replica would say, so your replicas are read replicas here, correct?
Yeah.
So then your read replicas would identify, it has not applied changes after this time. So it would go back and see, I am yet to apply this query. It would go ahead and apply it.
Some systems allow you to configure a write quorum, so you can, if you're really worried about your data, right? In that case.
Yeah. So if you have something like a write quorum where you would want that your write is successful only when your write is also propagated to a certain system, if you have that kind of thing, then your write won't even succeed unless it is written onto another replica. We'll be discussing that in next 15 minutes, how to have that. Okay. Yeah, Chandan?
Yeah, so this one use case of LinkedIn or Facebook, right? So when you have users from across globe, and we are sharing the data on the basis of, let's assume, countries like US people have the database, India. So then we have connections and friends from different countries as well, right? So and as we mentioned that we cannot do joins on different sites. So how do those things happen? Like if my connection isn't from US and he's posting a post on LinkedIn, even I am able to see that on my feed or something like that.
So the queries can go through it. Joins can't. Joins would happen. So if you have totally separate isolated databases, you can't have that. Typically, these kind of systems are scaled where your entire data is replicated. It's sharded but replicated. Right? It is sharded geographically, but data is replicated across countries. So there are multiple ways to tackle it. So when a company expands into a certain geography, they have an entire isolated setup about of their infrastructure. But typically the database still remains constant. So their database remains in their primary location. Okay. If they start with that they would want a separate database for that region. Let's say there is a guideline where Europe data cannot go outside. So then Europe needs a separate database. But now how will you able to query the data for Europe's user? Right. So then the query has to go to that database to get the data about. Data वहां से जाके लेके आते हो. So you would have a common place. You'd always need a common place to query all the things. Let's say with respect to LinkedIn, you'd need a place where you can query all kinds of data. Right. But the critical data of that user cannot leave the continent. If that's the use case, then that data won't leave the system. Uski query will go to that database.
Okay, so and there will be one database where, as you mentioned,
all the data.
All the data.
Yeah. Basically, a lot of companies have scaled it this way, but not a lot of queries go there. It's there to serve a certain use case, and obviously a lot of other things are scaled independently about it, because once you reach that architecture, you would have a lot of microservices. So each one is just taking care of a very tiny bit. So don't think about the entire LinkedIn's database is on just one database. It's typically a lot of isolated database handling just one single responsibility.
Yeah.
Let me just take one more question and then we'll move. Otherwise, aaj ka bahut late ho jayega. Vishal?
Yeah, so I'm not sure as to how multi-master would work. As to one master is there, right? I understand. But multi-master, so if I give a right, and a row gets added, then let's say there are two masters. So master one, master two. It will add to master one, or master two also would be having the same row.
No, it would add row to master one. Master one says my write is done. Master one would commit, right? And then similar to replica setup where the sync happens, the same query will be fired onto master two behind the sync. So eventually the same data will be available on another master.
Oh, okay.
So just imagine, instead of read replica pe only read queries going, here the masters are kept in sync. That's why I've written sync issues. So how will you keep data in sync between the two masters? So there are strategies like, for example, once a query hits a certain master, that same query after some time your other master gets synced, and then yahan ki query gets synced over here. So any write happening onto any of the master, behind the scene gets synced onto another master.
Okay. Fine. Yeah.
Let's jump into the next part, and I'll take all the other questions at the end of the session, like all this. Okay. Now we started about scaling relational databases, but now let's contradict ourselves and say why RDBs do not scale. Like, what's the general tendency behind it? Very simple way. RDS do not scale because they guarantee ASIC. Because it has so many things, like it guarantees atomicity, consistency, isolation, durability. If you add these many constraints, it is very hard for any system to scale, because it needs to ensure that while doing all the writes, none of the constraints fail and all of those things, right? So this is why your SQL databases are typically not scaling, because your foreign key constraints are there, right? And because of those foreign key constraints, you need all the data to reside on that one database, right? You need all the data to reside on that one node. If it is not there, you can't have cross database constraint checks. Otherwise, write would be terribly slow. Correct. That is exactly why your SQL databases are limited to that one machine where it can hold the data. That's why data sharding is also possible if your data is shardable. And then only you can shard the system. Otherwise, you would need this kind of things to ensure that your data is consistent. Even with multi-master setup, data consistency is a challenge. So you have to have a lot of checks on the application side to ensure that your data does not go into an inconsistent state. Right. SQL data. So that's why in read replica setup, what about write propagation? What would happen when your writes are happening? So your write propagation could be, it could happen in sync, where if your read replica setup is there and you are writing it onto the master, then you have two choices: either to do it on in sync, which means once my write happens on the master, I would immediately in synchronous, I'll write to the replica, which means I'm guaranteeing that even if my master goes down, I would have the backup of the data in other place. And in sync, which means your writes would become slower. Your database query, it would wait until the write has happened onto master and onto replica, and then it would say write is done. Right? It makes write costly systems a little slow. If it becomes async, which means my write goes to master, then slowly it gets synced to my read replica. Now what would happen is, if between this, between the event happening between these two, if between this my master goes down, I would not have, if the disk fails, entire disk fails, if someone drilled a hole into the disk, then my data is lost because my data never got a chance to get replicated onto my replica machine. Okay, so in read replica setup, always understand when would your data be, when should you apply sync and when should you apply async. Typically, when you are building systems from scratch, you would have to think about this sync, async. What kind of design choices would you make, right? In a multi-master setup, what happens to consistency? Consistency guarantees are lost in multi-master setup or anywhere where the partitions data is there, because that is exactly why NoSQL where there is no concept of consistency, because by default people assume the data is sharded, right? So in NoSQL databases, this is never a case, and you will always partition the data. Once you partition the data, you can ensure you can guarantee consistency within that partition, but not across partition. There are ways to do it, but very expensive. Not everyone recommends it. Right? Now scaling, until a certain limit, you would obviously vertical scale the database and then go into horizontal. Normalized data won't help. This is very important to understand. If you have a very heavily normalized data, which means no data redundancy at all, your system would succumb to scale. Your system would never be able to scale. That's why joins is something that prevents your database system to scale, because joins are expensive. Even with right sets of indexes, joins are terrible, but they give you very nice flexibility. So till a certain limit, joins would work really, really, really well. But after that limit, once you want to move to that next level, you'd have to give up on 3NF and add redundancy to the system. Like for example, with the tags one, you would have to add redundancy so that you avoid joins. Because after a certain stage, the number of joins would actually hog up your CPU and would not let your database scale after a certain limit. So you would add redundancy into your system. You would change your schema and let's say, if you know that your most frequent query is making join to the other table, you just fetch, let's take example of block that we were talking about. We know that the kind of query that we have been making is always on that by text on that tag wala thing. I'll just copy that tag field into another column over here and just let this query go through this only one table and don't have to join to another expensive table. Right. So instead of having too many foreign keys here or there, I'll just denormalize the data, which is exactly how your NoSQL works. If you see, your NoSQL is exactly like that. Where your data is sharded, you have denormalized data, a lot of heterogeneous data kept together in one place, right? So join, you would try to reduce joins, and that's how you'd attain scale. So joins across database is also not possible when it is sharded. And if it not possible, it is sharded. It is possible, but it is very expensive to do it, and a lot of thing has to done on the application end. Constraint spanning network database is not feasible. Like imagine consistency constraints you check, like how many database would someone have to put checks on, right? And obviously data model is not built to scale horizontally. So with respect to SQL, the way it is arranged, it is not meant to scale horizontally. That is exactly why you would go for NoSQL. But what if we eliminate joins and make data denormalized? It does help. Denormalizing data helps at scale. So identify your top queries. Always identify your top queries and see where you can denormalize. If you can denormalize, you're taking a little load on the application side to ensure consistency and all, but your database would scale. So RDBMS have been managed to scale because they've adopted NoSQL paradigms. So instead of having strict normalization, you are denormalizing data, which is more of a NoSQL-ish way of thinking, right? You have then sharded and isolated data, right? So through that, RDBMS have been able to scale. Cross database joins are possible but expensive, right? So these are something that you have to take care of. Yeah. Now coming back to our design problem, right? So what we'll do is we'll build our first storage engine. We'll build a SQL backed key value store. Here, it's not about how good our system is. Your key takeaway should be the kind of building blocks that we are choosing, or the kind of building blocks that we're discussing, so that you understand that this kind of architecture is possible, this kind of architecture is possible. And then you'll be able to make that conscious choice key, which one is better for what, right? So I'll be discussing some really interesting architectures that I have myself worked with. Not hypothetical. These are not unicorns. These are not mythical animals. These are some real, architectures that I have been fortunate to have worked on, and which would definitely add a great value. So, start grasping the building blocks and start asking critical questions to yourself. What would have happened if we would have chosen something else? Right? So, what we'll do, let's design a design a DB engine that is backed by SQL and acts as a key value data store. So we'll use MySQL, Postgres, any database, but what we would want is we would want to use it as a key value store, right? Something like Redis, right? A key value store, and we want to make it infinitely scalable. Obviously, otherwise, so I could have used Redis. So that's another challenge. We have to make it infinitely scalable. So again, what would be our decisions? How would the communication happen? What would be the constraints be? How would we model our database? What would be the features, concurrency, guarantees, scaling? How would scaling look like? This is the most interesting part that we'll be talking about. Then this is an interesting thing. If you see, Postgres database allows you to have JSON columns. And what if, and this use case is very similar to this. What if we allow indexing the data on a different key? So let's say in a key value store, if a value is JSON, you know that value is JSON, you can create an index on one of the attribute of that JSON, right? If you want to implement it. So this is similar to creating your own clustered index, right? How would you create that? So something that we discussed, we will use that part and build this thing, right? And then how about making range queries, especially at scale? Range queries, it's very simple, but when your data is sharded, how will our range queries work, right? And how will we build PTS? This is something that we'll be going to discuss during this entire course, into this entire design. Okay. Someone had a question. I forgot who it was.
Yeah.
Yeah.
I mean, if you want to use SQL as a key value sort of thing, I mean, the easiest way is to use a hash index, right?
Not index, but how would you model your database? What would be the challenges? Don't think from that perspective. Think about massive scales. Your one database would not work. No? What would happen? How would you scale that part? Any other concerns you also? How will you actually model your databases then? By using hash index, the same, na? Hash index all about.
Yeah. I mean, whatever is the key, I mean, just put key and value in the database and just, I mean, you create a index with hash index with the key.
Hash index with the key.
And that's all. I mean, you have a
that's
SQL
one
back.
system. Scaling it to the next level is where the challenge is and where the fun lies, right?
Yeah. I mean, the client side. I mean,
Exactly. It's very easy to model it, but it's very interesting to scale. So there are few architectures that would help us scale the system better. So why we picked a very simple example as key value store? Because key value store forms the simplest and the base to any database use case. So every NoSQL system that you see, like MongoDB, is nothing but a key value store, right? It's key value store with an ability to create indexes within the document. Correct. DynamoDB is a key value store. Redis is a key value store. So any database, if you typically see, is nothing but a key value store. So this is like the NAND gate of databases. So if you are able to design key value store, you can anyway model any other kind of databases on top of it. Right? You can build any database on top of a key value data. So that's why I've taken an example of key value store. It makes it easier to understand transaction, locking, read, writes, and patterns. Other NoSQL database are derivatives of key value store. Document database with ease can be implemented using key value store, right? That's why I'm more inclined, and throughout the course we'll take a lot of examples of key value store we'll be building around that, right? So typical example, REST API design. How would our communication be? Let's say our communication happens on top of REST. It's the easiest. You can build a TCP model, gRPC, anything. Let's take example of REST having a get, a post, and a delete. Get pay slash key, post pay slash key with data as the payload, and delete on slash key would delete the key. Right? As simple as that. Schema design, as rightly mentioned, what we have, let's say we have a table called store. It has a column called key. It has a column called value. It has, since we wanted to implement TTL, it will have a TTL and it will have a TS when the key was created, right? Now, with key, what do we want? With key, what do we want is, we want key to be the primary key of the table, because key is not, basically key has to be unique, right? So you would have to add additional checks around that. See, it should have regular expressions from, basically it says A to Z, 0 to 9, something, something. The value is a blob. Why a blob? Why can't we use any other thing? Why do we, or why should we use a blob here? Or can we use anything else?
And we want to support all types of data, so we actually went, I mean, it's a good design choice to use it as a blob.
Okay, support all data. Any other reason?
So Arpit, if you want to delete a key, we just need key and then value can reside at any place. So if we don't need value when you're like, let's say, getting the TTL or timestamp, or the key is deleted or not.
This value, right?
Yes. So it can be stored anywhere, like, no, because the length.
Acha, okay. Basically, it can be stored anywhere. I don't need to create clustered index on top of it. Something like that. Yes. I don't need to access value when I am performing operations.
Yes, because the 3 operations that you listed, all of them are on key only.
Perfect. So through this, I can skip the key point is, I don't want to have close affinity between key and value. So I can have value to be storing at any other place as in on any other disk page. I don't want it to be stored in a contiguous memory location as my row, right? So something like this database structure may, instead of, sorry, let me draw a better diagram. So if it's a blob, what would happen is key value something. So this is where my blob would be. And this is my key, this is my value will point over here. So instead of storing the 10 key B along the row data, because then my one row data would become massive, right? And I want to support bigger data chunks. I may be able to store indexes. I may be able to store images, videos, and whatnot into this database. Although we should not be storing, but we could be storing. So if we are doing that, it is always better, because I would never be querying on value. So it is always better to have this as a linked approach, where I'm just storing in terms of value, I'm just storing the reference to it in the table. So blob gives us that flexibility to do so. Right. Now TTL. So what would be stored in TTL and why? So let's say I have to put a value key K1 and I want it to expire in 10 seconds. Now what should my TTL hold?
I think you offset timestamp.
Offset from created.
Epoch.
Okay. I've heard three things. I've heard epoch, I've heard timestamp, and I've heard offset.
Arpit, we can go with integer only, because that will be efficient.
It's better. Chala, nice. We'll go with integer. And what will be stored? So I've given input as 10 seconds. Would I store 10 or what?
So everything might be stored in like seconds. Like we can decide that whether minutes will be converted at second or hour will be, like we can define it at
no, but let's say the input is always in seconds. Okay. And
now
the
time
finest
plus the expiration.
And the finest granularity I'm giving is 1 second. Okay. Now what should I be storing?
The insertion time plus the TTL expiration.
The final expiration time. Why?
because that's when we want to check if you want to expire the
But why not
stay or
just the
not. That's the
offset? But why not just the offset?
You have to read two columns then, like TS and TTL both.
Okay. So integer and then let's say final expiration time. So this is a great point. So the first design, in most cases, what we do is we don't really add this column, right? If we don't have a TS column, okay, if we don't know the created at timestamp and we just store the offset, it becomes impossible for anyone to find out when this value is going to expire. If we have timestamp column and we store TTL as an offset, as in how much time or how much seconds after this I want to do it. So then while running the job, I would have to go through all the rows. This is even worse. I have to go through all the rows to find out which ones are about to expire. Right? But if I have in TTL, if I store the final expiration time, I can just create an index on it and very efficiently apply a range query. Okay, order by this thing and in this range. Correct? Got it? Everyone got it?
Hey, can you please repeat that?
See, what would happen is our first approach that someone said was using the first word I heard was epoch, which means final expiration time. Okay. So if I let's say let's say to start with, what we'll be doing is, let's say we store let me do back. Okay, so final expiration. So let's say what do we store? We store TTL to be the offset. Okay, let's say 10 seconds. And then someone said that we would have to read TTL and timestamp, two columns to find out if it is expiring or not. Okay. Now, if you were to do this, now what would my job would do? My job would run, let's say every 5 seconds, and it would delete all the rows which are not needed or which are expired. Given this situation, what would happen is, how would I identify which rows do I have to delete? If I am storing offset in TTL and I'm storing timestamp of created I, how would I identify which rows should I delete? What would be the problem here? Is that I don't know. I'd have to go through all the rows to identify which are the ones that I have to delete, because every time I have to compute timestamp plus expiration, timestamp plus TTL is less than my current timestamp, then delete, otherwise not. Correct? I cannot efficiently use any indexes here, but instead, if I use in TTL, if I store the final expiration time, I can just do a range query on the TTL part where I'm storing the actual expiration time. If my expiration time is less than this, delete the rows. Clear? Full table scan versus index lookup directly. Yes, Risha?
Okay, so for this, right, can we sort of use you are thinking of utilizing inbuilt SQL based operations. What I was trying to see is like build a linked list and a map and try to sort of
you're building database now, where would you have that? Your SQL, your key value store has to be built on top of this. You can use a LinkedIn in this, but you can use a linked list and whatnot, but that goes into application side of code.
Okay, okay.
But now that also needs to scale, na? Because your linked list would become very big, your map would become very big.
Got it.
Got it.
Got it.
So you would want to work your way through. So this is a great decision that we have to take while designing a database. What should be stored in TTL and why? Answering that why is very important. Yes, Umar?
So like if we do not want to expire it, then like would we keep the TTL empty or sufficiently large enough for that?
Great question. You should ideally keep it null.
Okay.
If your TTL is null, because you don't want to, if you keep it sufficiently large, that time will come. Yeah. Hoping our company would work that part, but obviously that time would get anything that might happen would happen, right? Assume always that. So instead of having a very large value for that, you should always keep it null. Be on the safer side, keep it null. It's not going to expire.
Okay.
chart. A great DB design decision that we have to take. Like it's a very trivial use case, but there is always something fun there. Okay. Final field is deleted. Something that we discussed in the first week, but it's always good to reiterate. We'll always do soft deletes and then do a batch cleanup, like a defragmentation job of our operating system, right? So do that thing in one shot. Why? Because your database pages would be rearranged less frequently and in that one batch. A great example of this would be, let's say you have 3 pages in your database. So these pages are actually your disk blocks. Okay, and this is very important to understand when you are dealing with high throughput systems along databases, right? And on this, let's say you have 4 pages here, and let's say you have hundreds of keys, out of which you have deleted, let's say 8 keys, like this. 1, 2, 3, 4, 5, 6, 4, 5, 6, 7, 8. You have deleted 8 keys. So all these 8 lines marked in red are deleted ones. Now, if you don't do a soft delete, every time you delete a certain entry from the page, your B tree needs to be reorganized. Right? Once a B tree needs to be reorganized, it would be very painful, right? Because your database performance will take a hit because database CPU is there wasting CPU cycles on rearranging or rebalancing the B trees if needed, right? By doing soft delete, you are marking it as deleted. And then let's say one batch job is running, which deletes these rows permanently. Now, what would happen is it would, once it deletes something on a batch, so your delete query would be what? Delete where is deleted is true. So it would on the matching set of your where clause, it would match all of these rows together. Now your database engine would actually permanently delete these 3 rows in one shot. So, and would have to rearrange the B trees once for this page, once for this page, once for this page, and once for this page. So instead of doing 8 times rebalancing, it has to do it 4 times. Right? So these operations are batched. So these are actually operations running on your disk that will be batched by your database engine, depending on the query that you have fired. Right? So you're optimizing and batching the IO and not really incurring a massive performance hit by doing hard delete all the time. Okay, this is very important to understand as part of, when you're operating at scale. This is not something that you'll come across when you are doing it at like 100 requests per second something. Once you start hitting that scale, defragmentation is real. 4 days back, I defragmented a production database at the next. I did that. I had to run the defragmentation job to gain that performance. Then I did this very thing. And this gave me a performance. We always do soft delete and then hard delete after some time, and then defragmentation on top of that. And our performance boost by 8% out of the box. This is real. This you have to do when you attain scale. Right? So another approach to do is delete is another design pattern, right? This is very important. So understand the building blocks. Another design pattern is adding it to a delete buffer instead of is deleted. So if you say is deleted might be an overkill for a system where where entries are not deleted frequently. So what you can do it is, if your deletes are very infrequent, you can have a separate buffer, let's say an SQS queue, and you are putting your deleted calls, you are just putting the key there, deleting, this row is deleted, this row is deleted, and then you batch apply, and then you basically apply it in one batch. So this batch deletion job that happens on the database, you can actually do it on the application side. So let's say this kind of use case, having an external buffer would also help you, not do that action if required, or can help you do analytics on top of that. So there are some use cases that you can drive through this. So this is another pattern. If you are not there to use if you don't want to use is deleted as a column, you can basically model it separately using a message broker, right? And then slowly delete it from the database. Why this would be a little more performant in some cases? Because you are saving that 1 byte of space from every row which is being hogged by is deleted. Second, the index that you will be requiring on is deleted. So the cardinality of index is deleted is what? 2 unique fields, right? True or false. Right. So you are wasting that much of space on having that one index. So if you want to gain even that on the performance, your delete operation can just be a message push onto a delete buffer, and then which would slowly delete the data from the actual database. Okay, this is another design pattern that you can go for. Yeah, Ryan?
What you said about defragmentation, does it apply only to SQL or does it apply to
NoSQL also? Every database needs to go through defragmentation. Yeah, Ronak?
So in a write heavy system, like whenever we are deleting many rows like very constantly, in that case SQS will work, right? But if you are if you are observing that deletes are happening at a less number of times, then
But you should always, because you never know what operation can choke your database. So if your is deleted, if you have an is deleted column, always do soft delete, and during the VRs apply hard delete. Let's say when you have the minimum traffic, that's when apply the hard deletes.
Okay.
Always do that. Well, a delete operation have to be done soft delete and then hard delete at the later stage. Never do it in real time. You never know what might let your database choke into.
So my question was Arpit was when do we use this is deleted and let's say we have enough space, like we are not carrying off space as of now.
Then is deleted would work fine. You don't want to go for SQS and all. This is just a design pattern that you can go for. You can use it at other places. For example, let's say you want to delete something from your search index. Instead of directly applying delete operation on Elasticsearch, you can buffer it at one place and then reapply. So somehow, not even SQS, somehow buffer it at one place. Maybe create those many entries in a separate table. And then apply that, and then apply those, and then basically once a day, read that table and apply those changes.
But Arpit, in that case, a scenario will come that let's say our TTL is 5 seconds, like most of the rows. But if that's a lock will be applied again, like we have to update the is deleted flag like constantly. So
no. Case, you won't do that. We will discuss how to implement. So once your job runs, you can update is deleted flag. No problem there. But instead of doing that, you can always have that check when you are getting the key. When you're getting the key, handle it on the application side. If your TTL is already expired, you would say 404. We will come to it.
Okay.
Chalo. Guys, थोड़ा question बाद में लेते हैं. Thanks. बहुत लंबा design अभी है. चलो. Now what do we have? We have अपना user sitting. You have our server, some application code here, and our database, which is nothing but running our SQL, our key value engine, our SQL database. Okay. How do we scale this? When reads are high, right? You add read replicas. What happens if you want to scale writes? You scale up for some time and then you shard. Since it's a key value store, sharding is possible, right? Because your data will be mutually exclusive across your system, and all the operations are key based, correct? So you can very easily shard the system. So sharding would work really well because complete isolation would be there across system, and each shard will have its own set of replicas. So architecture is something like this, something that we discussed in the last slide. This is that in action, right? So all the operations are key based. Sharding is doable. So you have a user, you have your database server. Oh, sorry, you have your application server, which is taking in the HTTP request. You have two sharded database, let's say from A to M and M to Z, two sharded database, each database having its own set of read replicas. To scale, the reads going to that database, right? So now your application server would form connections with both the database. Depending on the key that it got, it would identify which shard or which database should I have to go to query. It would go to the database, fire the query on the corresponding read replica. If it's a get, if it's a put, it would apply it over the database and then do the job. Okay, this is a very traditional way to scale systems. Okay, now what happens is, this is a very interesting analysis. There is a very crisscross thing. Huh? Now what has happened is, our server overwhelms. So here we have just one server. Let's say now this server is overwhelmed. So what do we have? We have added one load balancer, because instead of having one server, we would always need our servers to be horizontally scalable. So what did we do? We added a load balancer here. Now this load balancer ke piche, we have two servers. Each server is creating connection to both the databases, and each of these sharded database have its own read replicas. Okay, this is a much complex architecture. Now, see the problem that this complicated architecture has introduced. What would happen is, for any key ke liye the request coming in, it can go to either server 1 or server 2, because load balancer is at random forwarding the request to one of the servers. Now, key, let's say for key A key request can come to S1 also or S2 also. So depending on where the request came in, the server has to query either database 1 or database 2. Oh, sorry, it would, oh, sorry. Since database 1 is always there for A to M, so S2 will have to make a connection to database 1. Similarly, if my request goes to request goes to S1, S1 have to make connection to database 1, right? So when my server basically starts up, all of my application server will have to maintain a connection pool to all of these data, to all the shards that I have in my system. Right? This is a problem. Why is this a problem? Because there might be, as my number of servers grow up, as I add more and more servers, each of the servers will make the connection to every single of my database out there. Right? Because any request of any key can come to any of my API server. This is a problem because now my database needs to be big enough to handle those many connections. Right? So now what do we do is, how do we change it? So this is not something which is seen in production, right? Not usually seen in production, but this is an architecture that you should be aware of. This is something that this is something that can be done, right? So what do we want is, since the problem is that because we have a single load balancer, because of the single load balancer, it is going to any of the servers. What if we split the load balancer? Something like this, but we add one common load balancer. Now these load balancers are not AWS offered load balancers or managed load balancers. These are custom load balancers. What would happen is, what do we want is that my API servers who are responsible to connect to a certain database, they are scaled as per the number of requests that it gets. Right? For example, here for my request for key ranges from A to M are quite low as compared to M to Z, also A to M and N to Z. Okay, so let's say my request for this is quite low as compared to my N to Z. Now what would happen is, in the first case, my number of servers, my number of API servers would be proportional to the total number of requests I'm getting. Which means even if my N to Z while a database is scaled up, has seen a lot of requests, my number of application servers are quite large, and all the servers are making connections to all the databases out there, which is a problem. Now to solve this problem, what we want is, we are splitting the responsibility such that the servers catering to a certain database are scaled only as per the number of requests they are getting that should go to the database. Let's say A to M wali request is just 100 requests per second, but this is like 10,000 requests per second for N to Z. So that would require just 3 or 4 servers to handle. Right. So now I can have a very smaller, and now why this is important? Because now I can have a smaller database for my A to M and a larger database for my N to Z. Right. I have independently scaling my databases. Right. Beforehand, in this architecture, the first one, in this architecture, what would have happened is, I would have to equally scale my both the database, because my database connections are becoming the bottleneck. Right? Because my database has to be big enough to handle those many concurrent connections. Even though they are stale, they needs to be connected. Right? In the worst case, all of them would connect. Right? So my database, instead of becoming that pain point, what I would want is, I would want total separation of controls. Right? Each database dealing with its own set of servers. Those own set of servers are scaled as per the requirements that are getting, or as per the traffic that it gets for the keys that it is responsible for. So we split the load balancers, and then I'll explain you where exactly is this applied. You'll be shocked to know this. Right? Now what we have done here is, for this database, this is responsible for A to M. It has its own pair of servers, has its own set of load balancer which connects from A to M. Right? This load balancer knows that I'm getting requests for A to M. So it forwards it to this load balancer. This load balancer then can freely and randomly assign it to S1 or S2. Right. So this is the load balancer. The first load balancer is the important one, which is intelligent, that it knows that my request is for this key, and this key lies in this particular sub-component of my architecture. And hence it would forward it to this load balancer, which in turn goes to this server and then to this database and to this replica if needed. Right? And then request for N to Z would go over here. So this first load balancer has to be intelligent one who is making that choice. Right? So this is a very simple example. Now, what would happen is, where is this used? DynamoDB uses this. So while I was working at Amazon, this kind of, I was really shocked to know this kind of argument. Like, why to add these many loops and all these many hops? But this is exactly how DynamoDB has managed to scale. Because if they don't do it, every system needs to be equally scaled. And this is exactly why they did it. Like every single data node had to be equally scaled up, right? Even though there was some random hot partition misbehaving. Here, basically N to Z is that hot partition which is misbehaving, as in getting a lot more requests compared to A to M, right? So when they had to scale it up, they had this architecture where they had multiple load balancer hops so that they can keep their cost at minimum and ability to independently scale up the system. So they don't use SQL obviously, but instead of DB, think about it as their data nodes, the way they have managed their data nodes. So they have this multiple hops of load balancer where each load balancer has its some set of intelligent logic written which understands, I need to forward request to this load balancer or that load balancer, and then it forwards it to that. It goes to that part of infrastructure and then gets up. Right. So this is not a traditional architecture that you'll use in day-to-day life. But if you operate at scale, this is a very plausible architecture which is obviously used in production. Okay. Any questions around this? I see Ryan and Srisha raising their hand. Is this one or old one?
Arpit, can you please repeat the last part? Mine was an old.
Mine was older. Achha, they're old. Okay, got it. Huh. So the last part is when do we need this kind of architecture? From that part, Srisha? The need of this architecture?
No, the last few lines that you said.
DynamoDB wala, right? Huh. So now when a certain, so again, why this kind of architecture is important is we are trying to utilize our resources to the best of our ability. Right? Because we don't want to over provision any of our data, not even DB1, not even DB2. Right? In the first case, we had to equally scale up all the databases because there is equally likely of a chance for the connection to be created across any of the database, right? With the later one, what we can do it is where we have ensured that the traffic from A to M goes into the top half of my infra, while the traffic from N to Z goes to the bottom half. I can scale my database D1, my DB1 to be just a 32 GB machine, while my DB2 could be 128 GB machine, right? So I'm not leaking money with this kind of architecture. I'm utilizing the database and my architecture to the fullest. So I'm not over provisioning my API server. That is still not that big of a problem, but database is more of a challenge for us. So splitting my load balancer helped us segregate the traffic. A to M goes at one half, N to Z goes to the other half, and the primary load balancer sitting at one.
Okay. So I'm not sure if this is a stupid question or it's already been covered.
It's not a stupid question. Please.
So, like, why can't you? So why not use API server level sharding? Like, if the API makes a call to the DB, the client automatically routes the request to a particular shard. So why not?
Which client? Database
so
client?
If like if on S3, if you use some client to connect to this DB, right?
Okay,
and
let's
make a query.
say from S3 is connecting to DTV, so S3 connected to DB2. So then you say that DB2 forwards the request to DB1.
No, it's like, let's say S3 maintains a pool of connections to DB1
That's the
and
problem
DB2.
now. Basically, that's exactly the problem.
Oh.
Because both the database, now let's say N to Z gets, let's say 5,000 requests. My A to M gets 100 requests.
Okay,
but my X1 and X2, when they start up, they would have to maintain massive connection pools with them. Na?
Understood. Yeah, makes sense.
Right? This is not something that happens on day one. This happens when you attain scale. Right? But this is an architecture that you should be aware of. Yeah, right? This is something that is possible. This is how we can utilize our structure well. This is something that I've seen working in production, and I was like blown away. I was just like 1.5 years old in the industry, and I was like, blown away by this thing. What kind of architecture is this? Right. Yeah, Pradman?
So the first intelligent load balancer would have a range, right? A to M and N to Z.
It would have everything. It would have A to Z.
And it would know
It
where
would have
to
that mapping.
Yes,
Yeah.
yes. So the map A to M would be some kind of a iterative range you are trying to say.
Yeah, something like range partitioning. Assume range partitioning from A to M goes to, so the anyhow you want to split it. Do it fixed key based or range partitioning or hash based, something.
That's my second question. So it could how would like it it makes sense on the integer side of things where you could easily range it out. But what happens when key is of something of a different range or some different
Cat speed में चलेगा ना? Cat speed would work. A to M, M to Z, and then you keep on splitting it in half if needed.
I didn't get, sorry.
So this string key would also work. Not only just integer, but even string would work. You can have sorting on that. Anything that you can.
Key has like assuming the key would be some letter word, right? Let's say a dog or cat or something.
Dog
like
is
that.
there, yeah.
So how would you range between this particular 3-letter word to a different?
So A to M is nothing but all the words starting with A to all the words starting with M.
Yeah.
So dog will fall under the first category.
Okay, so, so we can range it out on the starting.
Range it out on the basis of that. Yeah.
So, got it. Thanks.
Yeah. Vishal?
Yeah, so I wanted to know, I mean, if we keep on growing with this architecture, the network hops would be too much, right? The network latency.
Yeah. And that happens at scale. That does happen at scale, yeah.
Okay, in that case, then the edge and the pops would come in, right?
Yes. Then you will start utilizing your caches better. Your edge cache, then at all the level you will have some sort of caching. So you'll try to use cache very efficiently when it's scale.
Okay. So I mean, the idea should be to never to use or hit database in the extreme situations. Get data from cache itself.
Get data from cache itself. So you would try to minimize hitting your database. And that's what happens at scale. So if you see the cache hit ratio of, so the cache hit ratio at Netflix is close to 99 point some %. So most of the requests are like, for example, I was trying to build a product for search as a service. I reached out to Hotstar's VP and I was talking to him about the problem that I was addressing. I said that your search is not good. I can make it better. Right? He said, do you think we need search? The search is definitely not good, but giving them a better solution was not a problem because a lot of things were served from cache. Like for example, when you load the page or the first page, you'd see the item that most people have joined the platform to click. Like for example, Game of Thrones at that time, Game of Thrones season 8 or the final season was there. And the first thing that you see on the Hotstar's landing page was Game of Thrones, that episode. So you are bound to click on that. They have a very high cache hit ratio, very high. And that's how these companies scale, because they try to minimize data, or they try to minimize the hits going to the data.
Okay. So even in Google's case, in Google search space, right? So whatever we
cache. One fun fact. Why do you think Google introduced autocomplete?
Yeah, to
caching. Autocomplete is caching. Autocomplete, as in not autocomplete result is caching, but because once you hit that query or basically once you select one of the query which is suggested by Google can have just 10 documents or 15 documents, the document ID is being cached. It just goes ahead and fetches it. Right, so Google does not really, unless you type something and hit enter and not select from the autocomplete, Google might not even be performing search behind the scene. Think about this. So I typically leverage that to make unacademy search better. We introduced autocomplete. We decided to introduce autocomplete on a search queries to minimize the queries going onto Elasticsearch clusters and just serve the results from cache itself.
Okay, so for caching you use what?
Redis.
Okay, Redis.
So basically storing things pre-computed. That's the advantage you get out of autocomplete.
How do you update those results?
Once a day, something, or basically when the cache expires.
Okay, but
so go on.
In more critical cases like Google, where like if you make a query, you might get a new entry in your system, and it's very critical to the user. How would you like sort of make it
that
very
too
consistent?
will go to your search engine and get answered. Right? I'm just talking about how can you reduce the number of queries going there. Right. So one way to do it is, let's say if you have suggested, let's say 10 queries, when you type what and you suggested 10 queries, and let's say your user selects one of those which is suggested. Right. Once you click on that, Google could have already pre-computed top 10 results for that query. Right. So then Google does not really have to go to its raw search engine to make a search of that query across the system, because it has already pre-computed the top 10 queries for that, or basically cached the results of top 10 query, top 10 documents for that query.
Okay, let's say the cache expires every 15 minutes, right? And in
then
those 15 minutes,
it would go to the database and make it.
In those 15 minutes, what if you have like 20 records which came in and they sort of replace those 10 records? How would you, or is that like allowed for that kind of thing?
That's a really weird situation. So those 10 records are deleted and other 10 records. So typically you'd still see 404 pages on Google. Have you tried that? Have you seen a 404 page on Google? So when you search something, it shows you some top results, and if that page does not exist, when you hit that, it would still give you a 404 because that page anyway doesn't exist. It takes time for Google to re-index the data.
So, but in case of autocomplete, right? So let's say a course is on UPSC, right? So that is an autocomplete keyword for you guys. So in that case, how would you, store the courses on UPSC is a ID, or it will map to ID, and then ID you would be referencing to what?
Yes. So what do we have is, we store the UPSC, the actual search query in cache, right? So let's say UPSC is the most famous search query. So UPSC as a query is cached in Redis. Along with that, the value is nothing but 10 document IDs.
Okay, and then you fetch the ID
and
values.
What do we do? And then we just fetch the document IDs from the database. All the time, because people are bound to click on first and what, and if they go to the second page, then we make the search query. So we just try to improve the first performance or the first pursuit performance by the user.
So here the ID of the Redis is courses of UPSC. The full
and the entire query, the entire query. Yeah, the entire query.
Okay.
So one more doubt on this. When you said that you autocomplete, you show the user the auto-completed results. So does that mean like if the user uses that autocomplete or even uses the same query and puts it there?
If the user uses autocomplete, then only we fire it. So we don't fire it every time. Yeah.
Okay, means he has to select from the list down menus.
He has to select from the list that we give.
So basically that will fire a different API altogether.
That will fire, basically that fires, exactly. That actually fires a different API.
Okay. Yeah, I was trying that out. Even Google does that, something else.
Google does that. Exactly. See, everything is there in the network tab. You just have to open that up and just play around with it. See, the entire system design is this only. You just have to just keep your eyes open. This is how it happens. It's all there. Chalo, next question. Yeah, Vishal?
No, I'm done.
Yeah, Rajendra sir.
Hey, quick question. So this particular architecture is to eliminate the M into N connections between the servers and the DB connections. So just the way we have an intelligent load balancer at the API level, from a feasibility perspective, can something be implemented between the DB and the servers? Meaning, are there load balancers which operate at the DB level?
Yes, there are load balancers that can operate at database level, but they have just started gaining popularity. This kind of architecture might become redundant in next 10-15 years. There are great load balancers that sit between databases, and a great project is basically called as a proxy SQL. If you go to GitHub and search for proxy SQL, you will end up on a great GitHub repository, and we are actually using it in production. That's a great tool. That has that ability to sit in between and help you basically forward a request to some or the other database. Right. So
I
there
see.
are database. So basically, to answer it, just there are systems that acts as load balancer for your database.
Okay, great. Thanks.
Yeah.
No, but the read replicas thing is anyways load balancer, right?
Read replicas is load balancer?
When there are multiple replicas, right, and then you hit the replica address, one address, right? So it is anyways load balanced to one of the replica, right? If there are 3 replicas, it
If
will
you're
be
using
routed to.
if you're using Aurora or something which is load balancing your read replicas, then yes.
Yeah.
But here it's more about load balancing across sharded database.
Oh, okay.
Right, because some of your query has to go to DB1, some of the queries has to go to DB2. Right, that's right. But if it's independent, like it can go to DB1, DB2, it would not matter. Then that kind of load balancing would.
But load balancing across sharded database, then you will have to do all
Have
settings,
intelligent
right?
layer. Yeah.
A to M and M in N to Z and stuff.
Exactly. So basically, whatever Rajendra sir suggested was to move this load balancer here and have this thing here. Just move the have one load balancer sitting in front of both the databases, and that is intelligent.
Okay, got it.
Right? Final question before we move to the next one. Yeah, Brancho. Brancho, you have something to say?
Sorry, was speaking on mute. Am I audible? So, Arpit, if you can go to the slide a little top. So this one is not sharded DB design, is it?
These are sharded, na? DB1, DB2. This is from where we actually started. DB1, DB2, and then we added a load balancer.
They are storing keys like the sharded keys itself. The above
Yeah,
one.
these are A to M and M to Z.
Okay, I see. And
because that is where the problem is, because if you're getting too many requests for one database and not the other one, you're still creating database connections across.
Okay, and like maybe below one, the S1 and S2, which are the forwarded servers, right? Why do we have 2 over there? The reason for
These
that?
are normal API servers which are serving a request, like all the 3 get, put, post, delete APIs that we wrote. These servers are the one that are serving or that are handling that request.
But they're ultimately narrowing down to the single DB itself there, right?
So both of these servers, they connect to just one DB. So now I don't have S3, S4 connecting to DB1.
I see. So the number of concurrent connections is kind of
is the problem that we're addressing.
Okay, I see. Got it.
Sure. Final few things. Implementing TTL is something that we already did, but just to basically formally cover it. Approach 1 is running a cron job every T minutes that does soft delete, right? Or add it to buffer depending on the policy. But then what you also have to do, this is very important, check expiration when get happens, because for that T minutes until the next job runs, your database would still have entries pertaining which are expired but not yet soft deleted. You can't serve them. So this is done by DynamoDB. In DynamoDB, you can expire a certain key and you can still see the entry in their UI. But when you get it using code, it gives you that error that the item does not exist, right? Because there is this cron job running, which is run every n minutes, and then it is basically deleting or basically soft deleting the key. So what you should always do is you should always check when you are getting the key if it is expired or not, right? So approach 1 plus approach 2 works better. So you always have to handle some things also on the application side while ensuring that you have a cron job that deletes it. Like this is a great design. You don't want to miss out on those edge cases, right? Now implementing updates, all updates to key are full replacement. That always happens with key value store. Hence, while updating locks should be taken, locks are at low level. And since it's sharded DB, if Bennett scalar sharded DB, or even if it is not, it's just all the operations are happening on key level. So you'll always require row level locks. So you don't really have to worry a lot. If you have taken an exclusive lock on a row, that would solve the problem. If you have taken read locks, because anyway, all the operations of a certain key are happening on one row. So there is no major challenge there. If you just use basic locking mechanism, that would solve the problem for you, right? You can pick sharded lock, you can pick shared lock or exclusive locks depending on the situation. While reading, you don't really need any lock whatsoever because it's all operations are all in just one key, right? And since you don't have to have queries across multiple rows, so there won't be any big of a problem, right? So updates are rare. Exclusive locks are not recommended because exclusive locks would block reads from happening, and you would still want to serve reads at that time. The final thing, and a little weird, but a very important thing, is what if we want to implement slash list? You know, let's say a new operation slash list which iterates through all the keys of your system. Right? If it was one system, that was okay to do so. But when we have sharded system like this, how would your slash list happen through all the keys? Because it has to go through all the keys in this database and all the keys in this database, right? How would you model this thing? This is something that I specifically worked at Amazon. This was really gold when I found it. So doing a list operation, doing a scan operation on a sharded system, right? So how do we operate then? So let's say you are given a query, let's say K star. So every key that starts with K, I want to give that, right? So what do? Is we go to a load balancer. So our first load balancer would know key where does the key K star would lie in. It would know that it would lie into the KLF. It would lie into the first one, right? It would go there from the first load balancer. It would forward the request. Then that it would internally iterate through the SQL table like usual, and it would keep on returning things to the user. Okay. A very straightforward one, right? You can have pagination using limit offset or token based or whatever you would want to do it. That's a very straightforward thing. But now what if we want to have a scan star on this system, right? This is where the core design comes into the picture. How would you do it? It's the responsibility of the load balancer to handle it. So the front facing load balancer has to know when the iteration on one shard has ended and second one to begin with, right? So let me walk you through this. So here what would happen is you'd start from key A and you'll go till key Z. So all the requests would come to this load balancer. There's a slash list and it would know the last key that it's returned. So some way of pagination, right? The pagination strategy that would work the best over here is last key read something, right? It would always give me that something like what Twitter does with its API. It gives you the tweet ID, and then you can say that I want tweets after this tweet ID. Right? We would have to do something similar to this. Limit offset won't work here. What we'll do is we'll define a list operation such that it would start or it would take in as an input my last key that I read. Right? That key would be null at first. If it is null, it would go to the first load because this load balancer knows that my sorted key starts from here. It would forward it over here. It would go to any of the server. That's okay. And then it would, using this database, it would compute the first page. Let's say it got the first 50 keys out of it. Let's say the last key that was read was it started from J or something. So it would return the last key over here to the end user. So your user, when it wants to fetch the next page, it would say that I've already read till J. Give me all the keys after that. Right? Then it would send the next request. This load balancer would understand the array I've sent till J. When the user wants, this server would understand that I've sent till J. I want it. The user wants everything after J. It would go over here. It would fetch from J to M, and it would return. Right now the next request would come for N. The request it came from here for N. It would understand that N wala is over here. So it would forward the request over here, and then it would go over here. And then it would go back and the process will continue. Here, the key point to understand is how are we leveraging a different style of pagination to help your load balancer understand that the evaluation of your one shard is over, and then I have to forward my request to another shard. This is the important crux of logic that has to be implemented by this load balancer. And this is something that I have personally worked on. This is not a mythical animal. This is something that I've worked on. Right. So understand that now one edge case over here would be, let's say it received key K till M, because my load balancer would not know now my first shard is over, how would it know that this is ended its iteration? So while it is returning this thing, it should return something that helps this load balancer know that, okay, I'm exhausted. All the things that you wanted to iterate on is exhausted. You can forward this request to the next shard, right? So this needs to be communicated by this server, then to load balancer, then to primary load balancer, and it can internally forward the request to LB2. Let's say after this evaluation, once you request it for the next page, it just exhausted the first DB, but the request will go to LB1, right? So instead of returning an empty response to the user, which would mean that your entire iteration is over, your user should not get that. This load balancer would forward the same request to this LB2, and then it would fetch the next page, right? So defining how your pagination works would help us implement list operation across all the keys on both the database. A little complicated, but try to model it in your brain. Try to just devise or just write a very simple low-level code around this. It's not that difficult. It just
looks like dynamic programming. I mean,
yeah, something, right? Please continue.
This sounds like dynamic programming somewhat.
Dynamic routing.
Okay.
Right. So here, what we are doing is we are just doing routes. So what we want is, this is where the challenge is. We want our load balancers to understand where and sorry, my earphones are right. Huh. This is important because our load balancer needs to understand that where my system has to communicate something to the load balancer, and load balancer needs to take that intelligent decision to forward the request to another place. This kind of communication system is something that you have to establish, and the kind of pagination system that you will be using for this has to be last key based pagination, not limit offset. Limit offset pagination won't work over here. It won't scale. So the kind of pagination that you should be using is last key based, that I've read till this key, and you would always give your start key in your query, in your API request, that please start from till this key I've read, something like an exclusive start key. So I've read till this stage, give me everything after this. Right? This is how you will be setting up your protocol between your load balancers, your user, and your database. Yes, Piyush?
Yeah, so let's say we are reading it in J, right? So we have not read J entirely. So we would also have a key to ensure that we have read till this ID, right?
Obviously, yeah.
Yeah. Okay.
So you would have that. So typically, instead of having that till this ID, so you'll use that thing as your start key. So I've read till this thing. That will be an exclusive start key. So this terminology is used by DynamoDB. Right? It has this exclusive start key, and obviously DynamoDB is also sharded. It also has to implement something like this.
Got it.
Right. So when you're doing scan operations on DynamoDB, it goes through all the shards. It implements something like this.
Makes sense. Yeah.
Right?
Why can't we ask the client to send it? I mean, I did not understand. I mean, anyway, client has to page. So, I mean, why not ask the client, have the client?
Yeah, exactly. Client will page. But how will the client page? What kind of information would actually client give? Ki, I have read till this key. Right? Yeah. It needs to give that information. Na?
Okay.
Right. So that thing. So we have 5-6 different paging strategies. One of them is using limit offset. Right. That won't work here. Right. The best way to do this is, the paging strategy that we have to use is something that is last key based. I've read till this key, and this key will be given by whom? By our client, our user. Right. So user upon every request would say that I've read till this key, give me the next 10 keys. I've read till, and then once it read this 10 keys, then it would say, I've read till this key, now give me next 10. And then now give me next 10. It would, in the request, since REST is stateless, in every request, it would have to give you the start key from which you have to start iterating. Right. So now the input to your system becomes that start key. Now, once you get that start key, depending on the start key, your main load balancer will forward it to one of the two load balancers. That's it, forwarded to the first one. And then it discovered that, oh, my database one is exhausted. Well, I've already gone through it. And let's say you just read 3 keys. Your user requested 10 keys. Your request went to the first load balancer. and it just read just 10 keys, and basically it just got 3 keys out of it. Right now, how would you fill in the next 7?
Go to
Right.
the next shard, right?
Who will go to the next shard? The main load balancer would help you go to the next shard, because you would not want your user to see key only 3, and then because your user would think, "Arey, it's only 3, so then I'll just stop my iteration."
Yeah, but then why is that flag required? That okay? I mean, you said that there is a flag that it's exhausted because you already know from the. I mean, is it just for efficiency purposes when it exactly matches, or is it something?
No, but then how would you? But how would your load balancer know that it has exhausted? Malab, the next time, malab, using that thing, it's that edge case. When your first database, malab, you can do it like when your first database returns 0, then you start forwarding a request to the second database. You can do that. So somehow you are telling your load balancer that this is done. Right? You can do it with an empty result set. That is also okay. You can do it with a flag. So we typically did it with an error code, which was explicitly handled. So empty result set was sometimes possible. So we did it with a special error code which suggested that this is exhausted now. So you can forward all the requests going forward to this system.
Also, if you need maybe like 20 rows, if the client requests 20 rows and we have just at the last 10 rows of DB1,
first DB,
you still need to add the next 10 rows.
Yeah.
Yeah.
So a flag that communicates key first wala thing is completely done. So then otherwise you would have to change it to wherein when you got less than page size ka data, then you forward it to the next one. Isn't it is better that your database says that it is done, and that's it. Okay. And basically that is it for this one. So typical KV store was okay, but we just added a little twist to it to understand few very interesting architectures around this.
I had one question.
Yeah.
Regarding that this thing, right? Time limit which you put, like first we read it and then we get it, like on that slide, I think.
First we read it. This TTL one, na?
Yeah, TTL one. So you were saying like we should get the request, right? So check the expiration when get happens on the key. So this I didn't understand. Can you like?
This one. See, what do you have? You have a cron job. You have a cron job that runs every, let's say, 7 minutes. Okay. Every 7 minutes, it would go to the database. It would find all the keys that are expired, right? And then it would mark is deleted as true for them. Correct?
Okay. Yeah.
Now, what would happen between those 7 minutes? Jo keys that are already expired. When you make a get on that, you would still serve that keys, na? But typically those keys are already expired.
Yes.
So while doing that get, you should also check if the keys are expired or not, because this is the time when my next cron job is not kicked in. I have my is deleted is still false, but my keys are expired.
Okay. Okay.
Right. So basically that would be a time now, because during that cron ka duration, right, this will fail. That's why upon get you should always check for expiration. If the key is already expired, I would give it for a call.
Is there any edge case if it comes like suppose when he fetched the data, okay, and then it got expired, like he fetched the data and the time expired.
Data gone is gone. Malab, you would always fetch the data. Malab, it would just be like, but basically that is still not an edge case because you got the request before the expiration. If while you're making the request to the database, that's what matters, right?
Okay. Okay. So then that is like it's okay. Once
it's okay.
We
That's
get
okay. 1 millisecond se kya yeah. Okay. Chalo. Yeah, basically that's all. That was all that I wanted to cover. What we'll do tomorrow? Tomorrow will questions. Yeah, Piyush.
Yeah, so maybe this is a silly question, but in sharding, we can assume that all the databases would have, like all the shards would have exactly same number of tables, right?
Same number of tables.
Yeah.
Typically, yes.
Yeah. Okay.
Right? So the schema would remain same. The data would be mutually exclusive. Okay. Yes, Risha.
Could we have one more session on what you implemented at Amazon? I am really interested in that.
अरे कभी तो मिलेंगे ऐसे बहुत सारे trade secrets है but yeah I was just very curious while I was at Amazon. I just went through the wiki, who basically which team does what, when, why, how, what were the design choices. I did a lot because I had a lot of time spare at Amazon. Amazon is very slow in terms of that.
I feel that there's a lot of learning in that. That's why.
Yeah. There were a lot of learnings, especially with respect to skill, and that is exactly why I joined Amazon at that time. I wanted to know how things operate at scale and the kind of challenges that people have.
Yeah, definitely.
Yeah, that would be great.
Yeah, Umang.
So I just did not understand one thing. So this will only be applicable if I fire only a star query, right? If it is if it is a select.
Correct. So this is like implementing DynamoDB scan all.
Okay, but this is just for one use case.
Exactly. That's for just one use case. Yeah.
As in, if the query is like K star,
you'd only go to one database.
Yeah, but if it is just if it is like complete star, then only it will need to.
Yeah. For sure. See, likha hai pe, how to implement scan on star.
Okay, but as in it only just for one as in scan all के लिए पूरा इतना.
हाँ वो करना पड़ता है अगर पूछा है कि DynamoDB supports scan all.
Right.
Then so some developer has to code it now. So someone has to design it now.
Right.
So we क्या अपन ही करेंगे. Yeah, Rahul.
In the real time, can you give an example how sharding works? You just mentioned A to M and those kind of things. Real time, like how those data could look like.
This is exactly how it looks like. So when you have sharded, so the sharding happens on the application side. So application decides that this is my sharding key. So basically this is my sharding key. Where should the data go? Right. So the approach that we chose was a range-based partitioning, where I'm defining a range. From A to M goes to DB1, N to Z goes to DB2. Right. So this logic will be written where? On my application side.
Okay.
Right. So it will have connection. So in another example, the first one that we took, my application server has connection with both the databases. It got a request for a certain key. It would see कि अरे ये key कहाँ बैठती है with respect to my partition logic. Right. And then it would make a connection to the database and put the key there. And this is exactly how sharding works. No rocket science, very simple. Any other question, Rahul?
No, that's all.
Awesome. Yeah, Sandeep.
Yeah, but the custom logic is implemented in the load balancer, right?
Yeah.
To ship forward. So, how, I mean, the AWS provides some load balancer, right? So, will we be able to implement our custom logic?
We don't. We are not allowed to implement our logic on AWS's load balancer.
So, so any other load balancers in industry like that, or
Nginx, you can write your custom extensions and do that.
Okay, got it.
So Nginx HA proxy both supports that. If you're using service mesh, you can also configure that on that. Nice. Chalo. Vishal?
Yeah, so I wanted to know, in general, so this we are learning and discussing on system design. So, but on the high level system design, so what about lower level system design? What material, would you suggest?
Low level system. See, low level system design is mostly about what? Low level code on Java design patterns and all. That's all it is. This class, this object, singleton, that part. Adapter design pattern, factory design pattern, that part. No?
Yeah.
You can start with head first design pattern something. There is a great book. But if you're really into that low level design stuff, then go for a head start design pattern something. That's a great book.
Okay.
I have typically not worked on it for a very long time. That's why I don't typically cover low level design, and I'm not that keen on that part. I like this kind of challenges. So, but one book that I've definitely read, and I've read two books on design patterns. One is Effective Design Pattern or something. That's a red color O'Reilly book on design patterns. And second one was Head First Design Pattern. Head First Design Pattern was great one. It was fun to read it. It made things very simple to understand. So low level design with respect to classes designing and all, go for Head First Design first. Hands down. Great book.
Okay. And you also, I believe, read on the designing data intensive application, right?
Design data intensive application is a good book, not a great book. It's a very time consuming book. I had to skim through a lot of stuff because it teaches you distributed systems, not really applicable onto, our side of things. It has a lot of theory about something that we don't really use. I've never used it in industry, and not a lot of people would use it in industry. With respect to clock synchronization, the guy talks about like 6 pages for clock synchronization. Clock synchronization typically in real world is just one command that you set up as a cron. They don't really have to explain this big. I found it very redundant, but still, if you want to read it, don't read it like a textbook. Read something that you are interested to read about because it's a massive book. I've read it, but I've read it only the parts that mattered to me because I found it too redundant right from first page. So I don't recommend that book. For database internals, if you are interested purely into database internals, there is a book called Database Internals by Alex Petrov. That's a great book. Read it. मतलब मजा आ रहा था पढ़ के. That's a बहुत fun. It was quite fun to read that book. Database Internals by Alex Petrov. If you are into that. Distributed systems में data intensive application. Read it, but not as a textbook. Read the part that you're interested in.
Okay.
Yeah, Chandan.
Yeah, so a bit like all these concepts that we've learned related to relational databases, right? But still, when we have to make a decision which database to use when it comes to relational database like MySQL, PostgreSQL. So what are the parameters we keep into consideration? Because I was reading an article where Uber just shifted the database from Postgres to
Yeah,
MySQL.
that's a very famous one. Yes.
So so how does company decide like which relational database to go with?
Great question.
Yeah.
Great question. Thanks for asking that question. I always wanted to talk about this. See, typically database is the first choice that the company has made while starting up something. That database sticks for a very long time. Right? Typically, there are not massive changes between database engines. Like there are very specific features implemented by some. For example, MySQL versus Postgres. Postgres definitely gives you better performance than MySQL. But if your company started with MySQL and their monolith is on MySQL, you would continue to use MySQL for most of the cases. Right? Typically, it's the first person who makes that decision, right? Which one to use. Most cases in today's world, it's about getting that hosted service. Right? So AWS typically has that offering. So people typically go click. MySQL, everyone is aware of. Good documentation, go for MySQL. Postgres is a little sturdy, but great on performance, great on features. So there is this even split between MySQL and Postgres. Oracle, anyway, is proprietary, so people don't use it. Right? You would know the power of a database once you hit that scale. Once you seek a certain feature and it is missing from the database. For example, the way database handles caching. Right? So MySQL cache handling is very poor as compared to Postgres. MySQL analytics handling is very poor as compared to Postgres. If analytics is your use case, use Postgres. Right? So there are use cases that you want your system to handle. If you need an all-purpose or all-use general-purpose database, go for MySQL. It works well for all the cases. But if you have very specific use case, like my microservice would only deal with analytics and all, go for Postgres because Postgres is great at analytics. These are the things that you have to decide. But if you're looking for a general purpose, works for all, you can typically pick any. Most people pick MySQL.
Yeah, sorry. Can I go ahead?
Yes.
Yeah. So even when you build application, the way we talk to the database, either you use an ORM or you can write a SQL store procedure, and we can call that. So, like from your experience, what have you found more performant between these two, using an ORM or writing the SQL store procedure?
Start with ORM, faster, great developer productivity. Once you hit that skill, once you realize that ORM writes shitty SQL queries, right? That's when you move. That's when you start migrating from ORL to start writing your native SQL queries. Once you know that you are not writing good SQL queries, and now to get the next level of performance, then you move to stored procedures. That's typical evolution of a system. Right? Because ORM writes very shitty SQL queries. Everyone knows this. the kind of query that ORM, if it was not up to database engine to optimize the SQL queries, ORM would have been like long gone. The database optimizer, so the SQL query optimization of the execution plan creator is something that is still letting ORM, exist. It helps us like basically not write raw SQL queries and have multiple changes, makes it very codable with a certain language like Java with dot 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 karke you can do an autocomplete and do those stuff. It improves developer productivity because that's what you seek at first, but then you transition into writing core SQL queries on your own and then move to stored procedures and all. And that's what we have seen in the industry.
So on that part, like ORM is generally based on like provided as a language package, because I've never worked on it.
ORM is a library.
As in provided in the language which you are coding in, either Java or Python or.
You will find different ORMs for different languages. So database engine does not create any ORM.
Okay, got it.
Right. Database engine creates a bridge that will help you talk to, like for example, MySQL lib or basically MySQL client is something that database engine would give you. But ORM will use MySQL engine to connect to database. But ORM has a job to manage database connections, to build SQL queries for you, and export tables as native objects.
Okay.
I just had one question regarding this MongoDB and NoSQL databases, right? What's like a good use case for that? Like in large, is it used as hybrid system with along with relational database? Like I just wanted to know. Like,
if you know that you are going for sharding and if your data use cases is like that, like you don't see typically if you don't need foreign key relationships, if you don't have relations in your data, go for MongoDB, DynamoDB, any table like.
If there are a lot of reports and queries and all, then it is not
reports
preferred,
के लिए तो SQL, yeah. NoSQL पे you'll struggle a lot. I am struggling a lot making the design decision. For my personal project, I made a design decision of using DynamoDB. Now I want analytics on top of that, and I can't write queries on DynamoDB to do analytics for me because it's a key value stream.
No, what happens is like initially we start with MongoDB, right? Then the report part comes as a requirement. So that time it becomes like a bottleneck kind of like that.
It's a pain. It's a pain to write analytics query on NoSQL databases. I've made that poor design choice for my personal project. I know that, but I had to do it for cost reasons because DynamoDB is free.
Yeah, like previously we also had started with NoSQL, right? And then the report started coming as requirement. So that time like it was like a problem. Then we had to shift to this thing only, MySQL.
MySQL. That happens. See, this is live example. People say SQL, NoSQL, but SQL would save everything for you. It does analytics, it does normal purposes, logs, ACID, concurrency, and whatnot. NoSQL gives you sharding when you have schema-less documents. It still adheres to schema, but if you have schema-less documents, day one sharding, and you don't have a lot of foreign key use cases, go for NoSQL. Otherwise, SQL works the best. Yeah, Kaustuv?
So usually when folks are shifting between like one database to another, like how do they maintain availability at times like this?
They take a downtime. 100% availability is a myth. They take downtime, but you just might not see it because it happens when you're sleeping. That's it. A lot of companies go into database maintenance. Scheduled maintenance happen. That means you expect your systems not to be working. No downtime migrations happen with a lot of database, but not typically between SQL, NoSQL. There is a slight downtime, like 5 minutes, 10 minutes to 1 hour, depending on how big or how crucial the migration is. But that you have to take that plunge.
Oh, okay.
Right. Yeah, Piyush?
Also, this whole logic that we wrote for fetching the like the star queries, this can be used for the range queries as well, right?
Range query, yeah, you can use it. So if your range query is spanning across database, like K star is still okay. And if your range queries is like if your K itself is splitted across, right?
If you fetch from A to P, right? So because it is in both the databases, logic can be used there.
Nice. हो गया? Done. Thanks. Yeah, your code is really one. यार मस्त discussion होता है. I was lacking this. First code पे थोड़ा सा, second code not that much. This is really fun. Thank you guys for this. I'm having too much fun discussing things with you all. Nice. Tomorrow we'll dive into NoSQL. We'll build a very interesting use case. If you have not read about Google Firestore, go ahead and read about it. Just one line, give what it does, how it does. I'll still cover the basics around it, but we'll be building a very real-time database, right? Something like Google Firestore, and we'll see how it is designed. In this, we'll do WebSockets based connections and scaling things, right? बहुत सारा interesting fun is there scheduled for tomorrow's design. Okay, so see you guys tomorrow at 4. Bye bye.
Bye, folks.
Bye.